What if there are stars that don't burn, don't shine, and aren't even made of matter as we know it, yet still exist, massive and stable, somewhere out there in the cosmos? What if some of the black holes we think we see aren't black holes at all? Instead, they might be something stranger. Something more elegant. Something born not from fire and fusion, but from the whispering rules of quantum fields. These are Q-stars, quantum stars, one of the most mind-bending ideas to emerge from the intersection of astrophysics and quantum theory. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Q-stars are hypothetical celestial objects, unlike anything we've ever observed directly. Unlike the stars in the night sky, which blaze from nuclear fusion, or the dense remnants of dead stars, like white dwarfs and neutron stars, Q-stars are not built from matter in the conventional sense. They're not collections of atoms. They aren't powered by fusion reactions or supported by electron or neutron degeneracy pressure. Instead, they are stabilized by exotic scalar fields, continuous distributions of energy predicted by advanced quantum field theories. To understand what a Q-star is, imagine taking the concept of a star and rethinking it from the ground up, not as a ball of hot gas, but as a configuration of pure energy, arranged by mathematical equations and held together by the strange repulsive properties of quantum fields. These are not ordinary objects. They are not even made of particles, at least not in the traditional sense. A Q-star is a soliton, a stable lump of a scalar field that resists collapse because of its internal symmetry and conserved quantum properties. It holds itself together, not with atoms or molecules, but with equations. It's a star made of theory, structured by invisible energy fields. The Q in Q-star refers to a conserved global quantum number, often thought of as some abstract kind of charge that the scalar field carries. Because this charge is conserved, the configuration doesn't just dissipate or collapse under its own gravity. It's like a balloon filled not with air, but with a perfectly balanced field that knows how to resist gravity, not by pressure, but by the intrinsic properties of quantum mechanics. And what makes Q-stars especially intriguing is their potential mass. Unlike white dwarfs and neutron stars, which are limited by well-known thresholds like the Chandrasekhar limit or the Tolman, Oppenheimer, Volkoff limit, Q-stars could theoretically be more massive than even the most extreme neutron stars, without collapsing into black holes. This is due to the scalar field's ability to maintain equilibrium through non-classical, non-thermal means. In short, a Q-star could pack more mass into a smaller space, remain stable, and still avoid forming an event horizon. This places Q-stars in an extraordinary position in the spectrum of stellar remnants. They occupy the space between neutron stars and black holes, a territory that's mysterious and rarely explored. In this regime, classical physics starts to break down, and quantum effects dominate. And that's where Q-stars thrive. Another reason why Q-stars are compelling is that, from the outside, they might look almost identical to black holes. They would curve space-time strongly. They would produce intense gravitational fields. Light would bend dramatically around them. But unlike a black hole, a Q-star might have a surface, a real boundary, and not an event horizon. A spacecraft approaching a Q-star might eventually collide with this surface, rather than pass through a point of no return. This makes them extremely difficult to distinguish observationally, but also incredibly important. We might already be seeing them without realizing it. Q-stars blur the line between matter and field, between object and vacuum, between existence and theory. They're not stars in the traditional sense. They're not even entirely physical in the way we usually define physicality. They're quantum field configurations, stable, massive, possibly ancient, held together by the invisible scaffolding of the universe's deepest rules. They're like frozen waves in the fabric of spacetime itself. This isn't just theoretical play. The idea of Q-stars connects to real efforts in modern physics, especially in understanding how quantum fields behave under extreme gravity. Some versions of string theory, supergravity, and other advanced models predict the existence of scalar fields, and Q-stars provide one of the only astrophysical contexts in which those predictions could manifest as real, detectable structures. In the vast zoo of hypothetical celestial bodies, Q-stars stand out not because they are flashy, but because they are silent. They do not scream across the cosmos like quasars or explode in brilliance like supernovae. They wait, dark and quiet, possibly hiding in binary systems, possibly mimicking black holes, possibly forming in the early universe and lingering ever since. And if even one of them is real, it would revolutionize everything we know about matter, gravity, and the deep structure of space and time. To truly grasp the uniqueness of Q-stars, we have to set them against the familiar backdrop of known stellar remnants, white dwarfs, neutron stars, and black holes. These are the dense, final stages of stellar evolution, the collapsed cores of stars that have exhausted their nuclear fuel. Each of them resists gravity through increasingly exotic means, but they all rely on some form of matter behaving in extreme conditions. Q-stars, by contrast, are not only made of something fundamentally different, they follow rules that originate not from conventional matter physics, but from the delicate structures of quantum fields. A white dwarf, for instance, is what remains after a star like our Sun dies. It no longer fuses hydrogen into helium, but the residual heat and the incredible density keep it glowing faintly. Its collapse is halted by what's called electron degeneracy pressure, a quantum mechanical effect where electrons, due to the Pauli exclusion principle, resist being squeezed into the same state. But there's a limit to this. When the mass becomes too great, around 1.4 times the mass of the Sun, the Chandrasekhar limit, electron degeneracy pressure gives out. Exceed that, and the star collapses further into a neutron star. Here, the matter has been crushed to a point where electrons and protons have fused into neutrons, and now it's neutron degeneracy pressure that holds gravity at bay. Neutron stars are astonishingly dense, so much so that a single teaspoon of neutron star material would weigh billions of tons. But even they have a limit. Push them past around 2 to 3 solar masses, and even the degeneracy of neutrons can't stop the collapse. At that point, what remains collapses completely into a black hole, a region of spacetime so dense that not even light can escape its gravitational grip. Black holes are defined by an event horizon, a boundary beyond which nothing returns. Inside, general relativity predicts a singularity, an infinitely dense point, but this is where our physics begins to break down. We don't really know what lies at the heart of a black hole, only that it seems to erase all information about what fell into it, leaving only its mass, charge, and spin, a feature encapsulated in the famous no-hair theorem. Now enter the Q-star. Unlike any of these objects, it is not made of atoms, nuclei, or degenerate matter. It is not sustained by particle pressure, but by the coherent energy of a scalar field, something smooth, continuous, and fundamentally non-material. It doesn't follow the same rules because it's not made of particles packed together. It's more like a single, macroscopic quantum state. The entire star is the manifestation of a field rather than a clump of matter. This allows Q-stars to avoid some of the limitations of white dwarfs and neutron stars. They're not confined by the same degeneracy pressure limits because they're not supported by degeneracy at all. And unlike black holes, Q-stars don't form an event horizon. Their scalar field configurations allow them to be incredibly compact and massive without crossing that critical threshold where light can no longer escape. From the outside, a Q-star might mimic the gravitational field of a black hole almost perfectly. Light would bend, time would dilate, and nearby objects would orbit it as if it were a point of immense mass. But there would be subtle differences. If you could drop something toward it, you might discover a surface, strange, soft, and silent, where you expected to find an event horizon. That difference alone could change everything about how we interpret the compact objects we see in deep space. It's this fundamental nature of being a star not made of matter, but of pure field energy, that makes Q-stars so strange, and so compelling. Where white dwarfs and neutron stars push the limits of matter, Q-stars abandon matter altogether. Where black holes wrap themselves in an event horizon, Q-stars remain naked, yet still incredibly dense. They do not burn, they do not shine in the conventional sense, and they do not die in explosive finales. They are stable because of how quantum fields configure themselves, not because of what they're made of. In that way, they are more than just another kind of star, they are a completely different class of object. A reminder that not everything in the cosmos is built from atoms and elements. Some things may be built from rules themselves. At the heart of what makes a Q-star possible lies a concept so deeply rooted in quantum theory that it barely resembles anything from the world of classical physics. Unlike ordinary stars, which are supported by the collective behavior of countless particles, Q-stars rely on the structure and dynamics of something far more elusive: scalar fields. These fields, proposed in multiple branches of theoretical physics, are not made up of particles in the traditional sense. They are smooth, continuous values assigned to every point in space and time, like a universal ocean of energy that can rise or fall in strength from place to place. The quantum backbone of a Q-star is precisely this kind of field. Where white dwarfs are propped up by the stubbornness of electrons, and neutron stars by the stubbornness of neutrons, Q-stars are held together by a scalar field's ability to resist collapse through internal dynamics, mathematical relationships between field energy, spatial configuration, and quantum charge. These fields are not theoretical decoration. They're central actors in the fundamental workings of the universe. In fact, the Higgs field, the one responsible for giving particles mass, is a scalar field. If such a field can play a role in shaping the mass of every fundamental particle, why shouldn't other scalar fields shape entire stars? In the context of Q-stars, the scalar field doesn't just passively fill space, it actively interacts with gravity. As the field is pulled inward by its own gravitational attraction, it can configure itself into a stable soliton-like object, a lump of field energy bound together not by fusion or atomic structure, but by the balance of gravitational pull and field pressure. This is not pressure in the thermodynamic sense, like the hot gases inside our sun. It is pressure born from self-interaction, a pushback arising from the field's internal equations. Some scalar fields are designed in theoretical models to exhibit nonlinear behaviors. That is, the more they are compressed or concentrated, the more strongly they push back. This property is critical in stabilizing a Q-star. Without such self-interaction, the field might simply collapse under gravity, or dissipate into space. But with the right kind of potential energy, a mathematical function that determines how the field stores and releases energy, the scalar field can reach a balance point. The result is a structure with no atoms, no layers, no crust, just a massive, coherent energy configuration humming with quantum resilience. And this is where things get truly bizarre. In such a model, the field itself carries a conserved quantum number, often called Q, which is where the object gets its name. This conserved quantity prevents the configuration from simply vanishing. Just as electric charge or baryon number is preserved in normal interactions, the Q of a Q-star keeps the scalar field lump from decaying into nothing. It anchors the structure in the landscape of allowed physical configurations, giving it not just mass and gravity, but longevity. This quantum backbone also allows the Q-star to evade one of the cruelest truths in stellar evolution, the inevitability of collapse. Normal stars, even neutron stars, have upper mass limits. Add too much material, and no pressure, degenerate or otherwise, can stop them from imploding into a black hole. But Q-stars are not limited in this way. Their scalar fields can be finely tuned to allow stable configurations well beyond the mass of a neutron star, yet still short of forming a true black hole. In this narrow, strange region of possibility, Q-stars live, balanced not by the stuff of atoms, but by the subtleties of abstract fields. It's also worth noting that scalar fields, by their very nature, are the simplest kinds of fields imaginable. Unlike vector fields, like the electromagnetic field, which have both magnitude and direction, scalar fields are described by a single value at each point in space. This simplicity makes them ideal theoretical laboratories for exploring how fields and gravity might interact. And when those fields are curved by spacetime, or curve spacetime in return, they become candidates for building whole new kinds of objects in the universe. Q-stars are not just exotic for the sake of theory. They offer a working example of how gravity and quantum fields might co-create stable, massive structures that defy classical intuition. They don't need atoms. They don't need temperature. They need only the fabric of space, a scalar field, and the laws of quantum mechanics. In that trinity, they find their shape, their structure, and their extraordinary resistance to gravitational collapse. In the realm of physics, we're used to thinking about forces as interactions between particles, electromagnetism acting on charges, gravity pulling on mass, the strong force binding protons and neutrons together. These are familiar, even if they operate in exotic ways at cosmic scales. But scalar fields are something else entirely. They don't arise from particles pushing or pulling on each other in the traditional sense. Instead, they are continuous energy distributions that exist throughout space, and they follow their own strange set of rules that allow them to do something extraordinary: stabilize entire stars without using matter at all. A scalar field, at its simplest, is a mathematical quantity that has a single value at every point in space and time. Unlike vector fields, which include direction and magnitude, like wind velocity or the magnetic field, a scalar field just has a magnitude. You can think of it as an invisible temperature map over the universe, smooth, featureless to our senses, but powerful in its structure. The temperature in a room is a good analogy. At every point in the room, there's a number, a temperature, representing a scalar quantity. Now imagine instead of temperature, this value represents a kind of raw, quantum energy. That's the conceptual skeleton of a scalar field. One of the most famous examples of a scalar field is the Higgs field. It's an omnipresent field that gives particles mass as they move through it. But the Higgs is just one among potentially many. Some theories, especially those that go beyond the standard model of particle physics, such as supersymmetry, string theory, or theories of dark energy, involve other scalar fields that may be hiding in the fabric of reality. These fields could be relics from the early universe, or they might still be actively shaping spacetime today. So how do these fields differ from traditional forces? Most of the forces we know come with carriers, particles that mediate the force. For electromagnetism, it's the photon. For gravity, in some models, it's the graviton. These are vector or tensor fields, and their behavior is directional. They point, they wave, they move in complex ways. Scalar fields don't do this. They don't have a direction to push. Instead, they evolve quietly, altering the energy landscape of space in every direction equally. Because of their simplicity, scalar fields can behave in very elegant, and very strange, ways. Their equations of motion are governed by a potential function, which defines how the energy of the field changes depending on its configuration. Think of this potential like a landscape of hills and valleys. The scalar field wants to settle into one of these valleys, called vacuum states, but depending on the shape of the landscape, it can get stuck in a false minimum, or oscillate, or even spread out over vast distances. These behaviors are what make scalar fields so rich in possibility. Now, bring this back to Q stars. If a scalar field has the right potential function, say, a combination of self-attraction and self-repulsion, it can settle into a stable, localized configuration. This is called a non-topological soliton. In essence, the field forms a clump that doesn't decay, doesn't spread, and doesn't collapse. It's like a droplet of field energy hanging in the fabric of space, held together by its own internal dynamics. When gravity is added to the picture, this clump becomes even more fascinating. It warps spacetime, behaves like a massive object, and can reach densities comparable to neutron stars or beyond. But because it's not made of traditional matter, it doesn't succumb to the usual collapse mechanisms. Neutron degeneracy pressure, for instance, breaks down at high enough mass, leading to black hole formation. But a scalar field configuration can keep resisting gravity in non-thermal, non-degenerate ways. Its shape and stability come from the mathematics of its field potential and the conservation of its global charge. It isn't pushing back with particles. It's balancing itself, field against field, gravity against curvature, in a precise and highly stable way. This ability to maintain structure without pressure or temperature makes scalar fields perfect candidates for building ultra-dense, compact stars. Q stars are one such possibility, stable because the scalar field's configuration allows it. Not because it's burning. not because it's held up by quantum exclusion principles, but because the energy of the field finds a state where it simply doesn't want to change. The universe, it turns out, might have more than one way to build a star. It might not even need atoms to do it. In the known hierarchy of stellar collapse, neutron stars mark the last stop before total gravitational implosion. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own immense gravity. First, it may collapse into a white dwarf, supported by electron degeneracy pressure. If it's heavier, the electrons and protons are crushed together into neutrons, forming a neutron star supported by neutron degeneracy pressure. But beyond a certain mass, somewhere around 2 to 3 solar masses, even neutron degeneracy fails. The neutrons themselves can't resist gravity's pull, and the star collapses further, creating a black hole. This progression seems absolute, inevitable. An iron law of gravity and quantum physics working hand in hand. But Q-stars present a loophole. A whisper of rebellion against that gravitational fate. They offer a bold idea, that there may be another path. That it is possible to exceed the mass of a neutron star and still avoid the infinite darkness of a black hole. To understand how, we must return to the idea of the scalar field, the exotic substance that gives the Q-star its name. In a neutron star, gravity is balanced by the degeneracy pressure of densely packed neutrons. But even this quantum pressure has a limit. Q-stars, on the other hand, don't rely on matter at all. They rely on a quantum field configuration, one that isn't crushed or degraded by increasing mass in the same way particles are. The scalar field within a Q-star adjusts its distribution dynamically as mass increases. Instead of becoming denser in a way that leads inevitably to collapse, the field can reconfigure its profile, extending slightly outward, altering its amplitude, or shifting its internal energy balance. In this way, it absorbs additional mass not by fighting gravity with pressure, but by reshaping itself in accordance with its own field equations. This flexibility gives Q-stars a distinct advantage. They can hold more mass without collapsing because the internal mechanisms that maintain their structure are not based on particles being squeezed closer together. They are based on how the field resists changes to its configuration. And in some field models, this resistance actually increases with energy density, allowing the Q-star to remain stable even at gravitational strengths that would crush a neutron star into a singularity. There's another crucial factor, the absence of an event horizon. In a black hole, once a certain critical radius is crossed, the Schwarzschild radius, an event horizon forms. From that point on, not even light can escape. But Q-stars do not cross this threshold. They come close, but stop just short. Their scalar field configuration ensures that their gravitational potential, while enormous, never becomes infinite. There's no point of no return. No singularity. This allows them to fake being a black hole from the outside, distorting time and space dramatically, while still remaining a physical object with a definable surface or outer boundary. In fact, in some models, Q-stars could be as much as 10 to 20 kilometers in radius, comparable in size to neutron stars, but with masses that push the limits of gravitational collapse. It's a delicate dance. Too much mass, and even the scalar field might lose its battle. The exact threshold where this occurs depends on the specific field theory in question, its self-interaction potential, coupling to gravity, and conserved quantum number. But within the right parameters, a Q-star can remain stable beyond what neutron matter allows. This possibility opens up a new class of compact stellar remnants, objects that sit in the mass gap between the heaviest neutron stars and the lightest black holes. It's a region of parameter space that, until recently, seemed physically impossible. But Q-stars reclaim it. They suggest that the universe might host massive, compact, and stable stars that are neither neutron stars nor black holes, but something entirely new. Perhaps most tantalizingly, this idea suggests we may already have encountered Q-stars without realizing it. Some of the black holes detected through gravitational waves or inferred from X-ray emissions might not be black holes at all, but these elusive quantum giants masquerading as singularities. They would produce nearly identical gravitational effects, but up close, if we could get that close, they'd reveal a surface, a structure, a boundary. Proof that they are not the end of physics, but a continuation of it in a direction we're only beginning to understand. From a distance, the universe often hides its most profound differences behind a mask of similarity. In the case of Q-stars, this truth takes on a particularly deceptive form. These quantum objects, born of exotic scalar fields, are capable of imitating one of the most mysterious phenomena in all of astrophysics, the black hole. With immense gravity, extreme compactness, and a profound influence on spacetime itself, Q-stars can resemble black holes so closely that, from the outside, even light and matter may struggle to tell the difference. And yet, at the core of this resemblance lies a radical divergence. Q-stars possess no event horizon. This is the key. An event horizon, the boundary from which nothing, not even light, can escape, is the defining characteristic of a black hole. Once anything crosses this invisible line, it is lost to the universe. General relativity predicts that within this boundary, all paths lead inevitably to a central singularity, a point of infinite density where the known laws of physics crumble. But Q-stars, despite their incredible gravitational pull and compact structure, avoid crossing this boundary altogether. They manage to pack immense mass into a small volume, distorting spacetime profoundly, just enough to mimic the exterior gravitational field of a black hole, but they never collapse to the point of no return. This has dramatic implications. First, it challenges our current methods of identifying black holes. Most black holes are not seen directly but inferred through their gravitational effects on nearby stars or by the intense radiation emitted from material falling toward them. If a Q-star creates nearly the same gravitational environment, and if it too can pull in matter and generate high-energy emissions from accretion disks, then it might easily be mistaken for a black hole. The telescopes would see the bending of light, the orbital precession of nearby objects, the dimming of time as you approach the star. But without knowing there's no event horizon, it would be nearly impossible to tell the difference. Yet, theoretically, there are subtle distinctions, clues hidden in the edges of physics that could reveal the impostor. For instance, material falling into a black hole never emits a final flash from the horizon, it disappears. But for a Q-star, there could be a thin surface or outer layer of the scalar field. As infalling matter strikes this region, it might produce a faint but detectable burst of energy, something black holes would never do. These subtle emission signatures could be the fingerprints of a Q-star masquerading as a singularity. Additionally, Q-stars may have vibrational modes, oscillations of the scalar field structure, that differ from black holes. These could produce unique gravitational wave patterns in events like mergers. If two Q-stars collide, or if a Q-star merges with a neutron star or another Q-star, the resulting gravitational waves might carry signatures unlike those from true black hole collisions. Advanced detectors like LIGO and Virgo might one day be sensitive enough to distinguish these patterns, offering one of the few observational windows into the identity of such objects. Another possibility is timing. Pulsars, rapidly spinning neutron stars, emit beams of radiation with precise periodicity. If a Q-star were spinning and somehow emitting similar pulses, perhaps through interaction with its scalar field halo or accreted matter, it might also display timing characteristics that subtly differ from known pulsars or black holes. These timing irregularities could help distinguish Q-stars if we're looking closely enough, with instruments capable of measuring microsecond variations in pulse timing. It's also worth considering what lies beneath the surface, literally and metaphorically. Black holes are, in theory, hairless, a poetic way of saying they can be fully described by just three properties: mass, electric charge, and angular momentum. This is the essence of the no-hair theorem. All other information about the matter that formed them, including its composition, structure, and history, is believed to vanish behind the event horizon. A Q-star, in contrast, may retain a great deal more identity. Its scalar field configuration might encode subtle characteristics, internal structure, quantum charge, dynamic field interactions, that are not lost over time. This means that two Q-stars with the same mass and spin might still differ in their behavior, radiation, and interactions. They may not be entirely bald, so to speak. And that possibility cracks open the door to a whole new category of observational astronomy. Of course, these ideas are still deeply theoretical. Our ability to detect and distinguish such subtleties is limited by the precision of our current instruments and the distance of these objects from Earth. But with future advances, especially in gravitational wave astronomy and high-resolution imaging like the Event Horizon Telescope, these distinctions may come into sharper focus. There's also the philosophical dimension. The idea that something could appear, behave, and even influence its surroundings like a black hole but not actually be one forces us to reevaluate how we define objects in the cosmos. Are Q-stars stars at all? They do not burn. They do not fuse elements. They are not made of matter in the traditional sense. Yet they have mass, gravity, structure, and even a form of longevity. In many ways, they sit at the intersection of field theory and astrophysics, a living embodiment of the quantum world scaled up to stellar proportions. Their existence, if confirmed, would ripple through multiple fields of physics. For general relativity, it would pose new questions about the final stages of gravitational collapse. For quantum field theory, it would offer rare, observable consequences of scalar field dynamics. And for cosmology, it could imply that the universe is populated with far stranger objects than we've ever imagined. Imagine, for a moment, that some of the black holes catalogued by astronomers are not black holes at all. That their immense gravity is not coming from a singularity behind a horizon, but from a stable, horizonless mass of pure quantum energy. Imagine that the mysterious center of our galaxy, currently believed to be a supermassive black hole, is in fact a supermassive Q-star, hidden in plain sight, cloaked by the deceptive symmetry of its gravitational field. And if such objects do exist, they may not be rare. They could form under specific early universe conditions, or emerge from neutron stars whose mass slowly increases past their own stability threshold. Q-stars might be more common than we think, but harder to detect precisely because they pretend to be something else. They are the ultimate impersonators. Not through mimicry or disguise, but by being something that, in the eyes of the universe, simply looks the same. What's astonishing is that this deception isn't just physical, it's conceptual. For decades, we've trusted in the clear-cut progression from star to white dwarf, to neutron star, to black hole. But the Q-star refuses to fit neatly into that narrative. It hovers on the edge of collapse, surviving not by classical resistance, but by quantum equilibrium. It rewrites the final chapter of stellar evolution, not with a bang or a flash, but with a whisper. A balance. A stable quantum state that says, gravity has not yet won. The idea of Q-stars is not merely a flight of fancy spun from abstract speculation. It emerges from the deep and tangled fabric of modern theoretical physics, where gravity, quantum mechanics, and field theory all strain to coexist. This region of thought is not just where bold ideas are born, it's where mysteries gather. And Q-stars, these exotic, silent giants, sit at the intersection of our best attempts to make sense of a universe that is far stranger than we ever imagined. To trace the origin of the Q-star concept, we begin in the rich soil of quantum field theory. This is the framework that unites quantum mechanics with special relativity, treating particles not as standalone objects, but as excitations in underlying fields. These fields, electromagnetic, gravitational, scalar, fermionic, fill space and time completely, even in the absence of matter. Every known particle is just a ripple in one of these fields. And among the most mathematically elegant and physically mysterious of these fields are scalar fields, fields that assign a single value to every point in space. In the late 20th century, physicists began exploring what might happen if scalar fields themselves could form stable configurations. Could a clump of field energy remain bound together, resisting both dissipation and collapse? Could a field, instead of particles, form a kind of object in the universe? The answer, surprisingly, was yes. These stable lumps of scalar field were called non-topological solitons, localized solutions to field equations that held themselves together due to conserved quantum numbers. The theoretical groundwork for this idea was laid by researchers such as Sidney Coleman, who introduced the concept of Q balls in the 1980s. Q balls are field configurations that carry a conserved global charge, Q, and this charge provides the structure with stability. In other words, the configuration cannot just vanish, because doing so would violate conservation laws. These Q balls were originally explored in the context of supersymmetric theories, hypothetical models where every known particle has a partner, and they offered a new kind of matter, not made of protons or neutrons, but of field energy arranged in stable lumps. This was the beginning. But then, theorists asked, what if we added gravity? Enter the idea of Q stars. These are the gravitational counterparts of Q balls, massive, self-gravitating, soliton-like configurations of scalar fields. They were introduced in papers during the 1990s by theorists like Thomas D. Lee and Y. Pang, who explored how scalar fields with certain self-interaction potentials could resist collapse even under their own gravity. These weren't just oddball mathematical solutions, they were fully relativistic objects, behaving like stars, yet made of nothing resembling atoms. They were entirely hypothetical, of course, but that's where most of modern physics begins. The field equations governing Q stars arise from coupling Einstein's general relativity with scalar field Lagrangians, mathematical expressions that describe the dynamics of the field. The scalar field's energy momentum acts as the source of space-time curvature, just like matter and radiation do in standard general relativity. But unlike traditional matter, scalar fields can be configured in such a way that their energy density, pressure, and field oscillations stabilize the system. Under the right conditions, the field settles into a non-trivial solution, localized, massive, and horizonless. What's more, many versions of quantum gravity, attempts to unify general relativity and quantum mechanics, predict the existence of scalar fields. String theory, for instance, is filled with scalar degrees of freedom. In fact, the size and shape of extra dimensions in string theory are governed by scalar fields called moduli. Likewise, inflationary cosmology, the dominant theory of how the early universe expanded exponentially fast, is driven by a scalar field known as the inflaton. Scalar fields are not just an oddity of theory, they are deeply embedded in our most serious models of reality. This makes the Q-star idea incredibly compelling. If scalar fields are real, and if they interacted with gravity in the early universe or still do today, then objects like Q-stars could plausibly form under the right circumstances. They could have emerged shortly after the Big Bang, as pockets of field energy condensed and stabilized. Or they could be the remnants of massive stars that collapsed under gravity, but instead of forming neutron stars or black holes, transitioned into scalar field configurations. Perhaps the scalar field was always there, dormant and invisible, until the extreme pressures of collapse activated its strange stability. In recent years, the Q-star concept has gained renewed attention because it offers possible solutions to long-standing problems in black hole physics. For example, the information paradox, the mystery of what happens to information that falls into a black hole, might be sidestepped entirely if black holes don't form at all. If some or all black holes are really Q-stars, then information is never truly lost, because there is no horizon to hide it. The object has structure, identity, perhaps even memory. The quantum fields that compose it retain their configuration over time, meaning the universe doesn't erase its own history quite so completely. There's also the growing realization that compact objects without horizons, like gravastars, Boson stars, and Q-stars, can produce gravitational wave signatures nearly indistinguishable from black hole mergers. This places them on the radar of current and future observatories, such as LIGO, Virgo, CAGRA, and LISA. Each of these instruments is capable of measuring the tiny ripples in spacetime caused by cosmic collisions. And if those ripples deviate even slightly from black hole predictions, through echoes, cutoffs, or unusual damping, they could point toward the existence of something even stranger. In this way, Q-stars are more than just speculative. They are part of an active theoretical landscape, a bridge between quantum field theory, general relativity, and cosmology. They are one answer to the deep question, what kinds of objects are truly possible in this universe, when we consider all the forces at play? And perhaps, most beautifully, Q-stars challenge our instinct to think in binaries. Not all stars burn. Not all massive objects collapse. Not every endpoint must be a black hole. Somewhere between matter and vacuum, between particle and wave, between gravity and geometry, lies the Q-star, a silent compromise written not in fire or fusion, but in the language of fields. The question that inevitably follows the introduction of Q-stars is both simple and profound. Could they really exist? It's one thing to construct elegant mathematical models of exotic objects within the safety of theory, but it's another thing entirely to argue that such entities actually populate the cosmos. Are Q-stars just theoretical curiosities born from speculative field equations, or are they genuine residents of our universe, quietly lurking in the darkness, masquerading as black holes or unexplained compact objects? To address this, we must weigh the evidence, both the supporting arguments and the skeptical counterpoints, with an eye on the physics, the cosmology, and the observational frontiers. To begin with, one of the strongest arguments for the possible existence of Q-stars is rooted in necessity. Scalar fields are not a fringe idea in physics. They are mainstream, even essential. The Higgs field is a scalar field. The inflaton field that drove cosmic inflation is another. Many theoretical frameworks that attempt to unify gravity with quantum mechanics, such as string theory, predict a rich landscape of scalar fields permeating the universe. If these fields exist, and there is no strong reason to believe they don't, then the configurations those fields can take, including stable, localized structures like Q-stars, are not only plausible, but expected. Moreover, the scalar field configurations that give rise to Q-stars are stable solutions to the Einstein-Klein-Gordon equations, which couple general relativity with scalar field dynamics. These solutions are not just mathematical oddities. They are energetically favorable under specific conditions and do not rely on exotic physics beyond what is already theorized. In fact, if scalar fields with the right self-interaction potential exist in nature, then Q-stars might be among the most natural outcomes in high-energy environments like the early universe or the core collapse of massive stars. There is also an observational gap that Q-stars may help fill. Between the heaviest known neutron stars, about 2.1 solar masses, and the lightest confirmed black holes, typically starting at around 5 solar masses, there exists a curious mass gap. Few, if any, confirmed compact objects fall into this intermediate range. It's an open mystery in astrophysics. Could Q-stars occupy this gap? Since they are more massive than neutron stars but lack the event horizon of black holes, they may sit perfectly in this no-man's land, quietly being misclassified due to the similarity of their gravitational effects. Q-stars also provide a compelling alternative to resolve some of the most vexing paradoxes in physics. For example, the black hole information paradox, the apparent loss of quantum information in black hole evaporation, poses a serious challenge to the principles of unitarity in quantum mechanics. If Q-stars exist and replace some of the objects we currently believe to be black holes, then this paradox might not even arise in those cases. Information may never be lost behind an event horizon because the horizon never forms. Instead, information might remain encoded in the scalar field configuration of the Q-star, preserving quantum coherence. Further strengthening the argument is the increasing sophistication of gravitational wave detectors. Mergers between black holes produce precise waveforms, but alternative objects like Q-stars might yield detectable deviations, subtle echoes, late-time ring-down anomalies, or missing quasi-normal modes. Though current data is limited, the possibility that gravitational wave signals might eventually betray the presence of Q-stars cannot be ruled out. And yet, there are serious challenges to believing Q-stars are real. The first and most obvious counterargument is that they are entirely theoretical. No Q-star has been directly observed. While their gravitational effects might mimic those of black holes, we lack any definitive electromagnetic signature, gravitational wave anomaly, or surface interaction that can distinguish them conclusively. Their very nature, horizonless yet ultra-compact, makes them difficult to confirm. If they behave exactly like black holes in most ways, then even if they exist, we may not yet have the tools to recognize them. Another issue lies in the model dependence of Q-stars. Their existence hinges critically on the presence of scalar fields with very specific self-interaction properties. The field must be stable, non-dissipative, and capable of forming solitonic configurations under gravitational pressure. This places constraints on the kind of field potentials that could work. In turn, this restricts the class of theories in which Q-stars are viable. Without experimental verification of such scalar fields, beyond the Higgs, we are leaning heavily on theory to justify these objects. Moreover, astrophysical formation mechanisms for Q-stars are still speculative. While it's tempting to assume that they might form in the early universe or during stellar collapse, the exact conditions required for a scalar field to dominate over traditional matter are unclear. What kind of star would become a Q-star instead of a neutron star or black hole? Would the scalar field spontaneously switch on during collapse? Would it need to be seeded somehow during inflation or reheating in the early universe? These questions remain unresolved, and until we can describe clear formation pathways, Q-stars risk remaining abstract entities with no real cosmic factory. Additionally, from a particle physics standpoint, we still lack direct detection of any scalar particles beyond the Higgs boson. If the fields responsible for Q-stars exist, where are the particles associated with them? Why haven't we seen signs of them in high-energy experiments, such as those at the Large Hadron Collider? The absence of such particles casts a long shadow over scalar field-based astrophysical objects, though one could argue that the mass scale or coupling strength of these particles simply lies beyond our current detection threshold. Another concern comes from the simplicity of black hole models. Black holes, for all their mysteriousness, offer a remarkably elegant solution to Einstein's equations. They require no additional fields, no speculative matter, no fine-tuned potentials. In contrast, Q-stars require a more elaborate setup, a custom field, a stable potential, a global quantum number to stabilize the configuration. In the absence of observational pressure to consider alternatives, many physicists prefer the simplest viable model. In that light, black holes are favored not because Q-stars are discredited, but because Occam's razor cuts against them. Yet, physics is not ruled solely by simplicity, it is ruled by truth. And the truth is, our universe remains full of unknowns. Dark matter, dark energy, and the earliest moments of the Big Bang all hint at the presence of physics beyond the standard model. Scalar fields are embedded in our best explanations of cosmic evolution. Q-stars may simply be the gravitational embodiment of those fields, real objects whose existence has not yet been revealed by light or wave, but whose footprints may be found in the next generation of observational data. In the end, the case for Q-stars lies in a delicate balance between theoretical richness and empirical silence. We know they could exist. The math allows it. The physics welcomes it. The universe, as we understand it, does not prohibit it. And that alone makes the pursuit of evidence not only worthwhile, but essential. To fully appreciate the place of Q-stars in the theoretical zoo of compact stellar remnants, one must look at their close cousin, an equally strange and captivating idea known as the boson star. While Q-stars are stabilized by scalar fields with a conserved quantum charge, boson stars are formed from actual quantum particles, bosons, which are the force carriers of the universe. These stars represent yet another route the cosmos might take in defying gravitational collapse, not by piling up neutrons or conjuring an event horizon, but by weaving a coherent dance of quantum particles that collectively form something star-like, yet wholly unlike anything we see in the sky. Boson stars are built on a fundamental quantum truth. Bosons, unlike fermions, are not subject to the Pauli exclusion principle. That principle, the rule that no two identical fermions can occupy the same quantum state, is the very thing that underpins the stability of white dwarfs, with electron degeneracy pressure, and neutron stars, with neutron degeneracy pressure. But bosons play by different rules. They can all pile into the same state, perfectly overlapping, forming what is known as a Bose-Einstein condensate. In a lab, this gives rise to exotic forms of matter at near-zero temperatures. But in space, under gravity's watchful eye, it opens the possibility for stars made not of heat or pressure, but of coherence. Imagine, then, a cloud of bosons in the early universe. If they are cold enough, light enough, and weakly interacting, they could collapse under gravity into a compact, coherent state, a boson star. These objects would be extremely dense, have no surface in the conventional sense, and could, depending on the type of boson, range from microscopic to supermassive in scale. Like Q-stars, they would lack an event horizon. And like Q-stars, they would challenge our definition of what it means to be a star. But here's where things get interesting. The underlying field that supports a boson star is a complex scalar field. That is, the same kind of field involved in Q-stars. In fact, many models of boson stars and Q-stars use similar mathematics. The difference is largely in interpretation and emphasis. Boson stars are often treated as macroscopic quantum states of a large number of actual particles, bosons, that have condensed into a single quantum wave function. Q-stars, on the other hand, are usually modeled as solitonic configurations of a scalar field, where stability arises not from the number of particles, but from the conserved global charge of the field itself. In practice, these two concepts can blur. Some Q-stars could be viewed as boson stars with particularly strong self-interactions. Others may arise from theories where bosons themselves are excitations of a fundamental scalar field. In this way, the difference between a Q-star and a boson star is not one of substance, but of context. It's a question of whether we're talking about the coherent behavior of quantum particles, or the classical configuration of a field. The border between them is thin, and in many cases, purely mathematical. This connection deepens when we examine the specific types of bosons that might play a role. While photons and gluons are bosons, they are massless and not suited for star formation. But hypothetical bosons like the axion, a particle proposed to solve the strong CP problem in quantum chromodynamics and a candidate for dark matter, are prime candidates for forming boson stars. Axions are light, weakly interacting, and expected to exist in enormous numbers. If they form condensates in the early universe, they could collapse into boson stars, or Q-star-like structures. The resemblance doesn't end with formation. Both Q-stars and boson stars are predicted to be extremely compact, with densities rivaling or exceeding those of neutron stars. Both would warp spacetime significantly, creating gravitational fields similar to black holes. And both are thought to exist in a variety of masses, depending on the properties of their constituent field or particles. Mini-boson stars, formed of ultralight particles, might be no more massive than a small asteroid, but supermassive versions could rival the black hole at the center of the Milky Way, all without an event horizon. So could Q-stars be boson stars, or vice versa? The answer is possibly. The classification often depends on the level of abstraction. In one model, we may describe a compact object as a field configuration with a conserved charge, thus calling it a Q-star. In another, we may describe it as a coherent state of many bosons, thus calling it a boson star. The mathematics overlaps. The field equations look similar. The properties converge. This suggests that both objects may be manifestations of the same underlying reality, quantum matter or energy structured into stability by gravity and self-interaction. One area where they diverge slightly is in the role of quantum mechanics. Boson stars are explicitly quantum objects. They involve superpositions, condensates, and wave function coherence on a macroscopic scale. Q-stars, though quantum in origin, are often treated as classical field solutions, the stable shape of a scalar field in curved spacetime. This distinction matters when we ask how these objects evolve, radiate, or interact with their environments. For instance, a boson star might undergo quantum transitions, emit discrete quanta of radiation, or collapse due to decoherence. A Q-star, being a classical configuration, might behave more like a traditional soliton, only breaking down if external conditions disrupt its internal balance. Yet even here, the difference may be a matter of scale. At sufficient distances or energy levels, the quantum behavior of a boson star may become effectively classical. And a Q-star's classical field may, under magnification, reveal its quantum skeleton. They are not opposites, but reflections, different ways of describing the same phenomenon, the stabilization of gravitational collapse not by matter, but by force. This link has deep implications for astrophysics and cosmology. If Q-stars and boson stars are two faces of the same coin, then the search for one is also the search for the other. The gravitational waves we detect, the dark objects we study, the mass distributions we chart across galaxies, any of these could carry the signature of a scalar field object. We may already be observing them without realizing it. And perhaps most intriguingly, the boson link places Q-stars within a wider cosmic context. If the dark matter of the universe is made of bosons, especially ultralight axion-like particles, then it is conceivable that a small fraction of that matter has clumped into boson stars or Q-stars over cosmic time. They could be hiding in dark galactic halos, orbiting quietly, or occasionally merging to produce brief, detectable flashes in the gravitational fabric of space-time. In the grand tapestry of physics, then, Q-stars and boson stars are not isolated threads. They are woven together, one emphasizing fields, the other emphasizing particles. But both remind us that the cosmos may construct itself from building blocks far stranger than protons and electrons. It may sculpt stars not from flame or plasma, but from waves, from symmetry, from coherence. And in doing so, it may leave behind structures as stable as stone, yet as ghostly as thought. At the heart of the Q-star's extraordinary nature lies something far more fundamental, and far more peculiar, than atoms, neutrons, or even familiar forms of energy. These stars are not built from ordinary matter at all. Instead, their existence hinges on what is often referred to as exotic matter, a category that includes strange, hypothetical particles not found in the periodic table, not forged in the hearts of stars, and not observed in any particle detector to date. These particles live on the speculative frontier of physics, and among the most intriguing candidates are scalar bosons, particles whose behavior defies the common rules that govern the matter we are made of. To understand why these exotic particles are necessary for Q-stars, consider the limits of conventional matter under gravity. In normal stars, outward pressure from fusion balances gravity. In white dwarfs, electron degeneracy takes over. In neutron stars, it's neutron degeneracy, fermionic pressure resisting further compression. But beyond a certain mass, even that fails. The object collapses into a black hole. Gravity wins. Unless the material resisting that collapse isn't matter at all, but an exotic field configuration. That's where scalar bosons enter the picture. Scalar bosons are particles with zero spin, unlike photons, which have spin 1, or electrons spin 1/2. They are fundamentally different in how they interact and combine. Most importantly, they are bosons, which means they obey Bose-Einstein statistics. This allows them to pile into the same quantum state without exclusion. If enough scalar bosons are present and interacting through the right kind of potential, specifically, one with self-interaction terms, they can create a coherent field, one that is smooth, stable, and self-contained. This field, under the influence of gravity, can condense into a compact, stable configuration, the Q-star. But what kind of exotic matter could do this? One promising candidate is the axion, a hypothetical, ultralight scalar particle proposed to solve the strong CP problem in quantum chromodynamics. Axions are also one of the leading candidates for dark matter. If axions exist and are abundant in the universe, they may naturally form field configurations through gravitational attraction and quantum coherence. Under the right conditions, axions could produce either boson stars or Q-stars, depending on their interaction strength and the field's conserved properties. Another possible candidate is the dilaton, a particle that arises in string theory and modulates the strength of interactions. Dilatons are scalar fields, and if they are light and stable enough, they too could clump under gravity. Similarly, moduli fields, scalar fields that determine the size and shape of extra dimensions in string theory, could act as the building blocks of exotic compact objects. These fields have long been predicted by higher dimensional theories, and although they remain hidden, their gravitational footprints could manifest as Q-star-like objects. In more speculative theories, entirely new scalar particles could exist, with properties tailored to create Q-stars. These particles might have masses far below those of known particles, with ultra-weak interactions, Or they might exist in hidden sectors, realms of physics that interact with our observable universe only through gravity. The idea that the universe has multiple sectors of matter, each with its own set of particles and forces, is a common theme in modern physics. Some versions of supersymmetry, for example, predict mirror sectors or shadow matter filled with exotic particles. Q-stars, then, become a kind of gravitational laboratory for these hidden sectors. If exotic matter exists, we may never see it directly in a collider, but we might observe the structures it forms under gravity. And because these structures behave differently from black holes, they offer a potential way to test the existence of exotic particles without needing to produce them on Earth. What makes these particles truly exotic, however, isn't just their unfamiliarity. It's the way they interact with themselves and with gravity. Ordinary matter experiences attractive gravity and repulsive quantum pressures, like degeneracy pressure. But scalar bosons in a Q-star may experience both attractive and repulsive self-interactions within the field itself. These self-interactions are governed by the shape of the field's potential, a mathematical function describing how the energy of the field changes with amplitude. For a Q-star to exist, the scalar field's potential must have a form that allows for stability. This usually means the potential has a, shape, a minimum where the field can sit stably, surrounded by energy barriers that prevent it from dissipating. The field must also support localized solutions, meaning it must allow the energy to clump together without immediately radiating away or collapsing. These requirements place strong constraints on what kinds of exotic matter can form Q-stars. There's also the role of global charge. Many models of Q-stars assume the scalar field carries a conserved quantum number, often labeled, such as particle number or a type of field charge. This conserved charge acts as a stabilizing factor. It's like a quantum anchor that keeps the configuration from evaporating. The more charge the Q-star carries, the more stable it becomes, up to a certain limit. Beyond that, gravitational forces may overwhelm the field's stability, and the star may collapse into a black hole. This charge is crucial to distinguishing Q-stars from boson stars. While both rely on scalar fields, Q-stars are specifically defined by the presence of this conserved quantity. It's what gives them their name. The Q in Q-star stands for the conserved quantum charge. This property adds a new layer of structure and identity to the object. A Q-star is not just a blob of field energy held together by gravity. It's a charged, coherent configuration, with an internal structure shaped by the delicate balance of gravity, field energy, and quantum conservation laws. In all of this, the role of exotic matter is not passive. It doesn't merely replace neutrons or protons in some cosmic recipe. It changes the entire game. With exotic matter, gravity is no longer the ultimate arbiter of stellar fate. It becomes one player in a more complex interaction, a negotiation between curvature, coherence, and conservation. The Q-star is the result of that negotiation. But the presence of exotic matter doesn't only reshape astrophysics. It also reshapes our vision of the universe. If Q-stars exist, they are made of stuff that is all around us, yet invisible. The same particles that may constitute dark matter halos, drift silently through our galaxies, and evade our detectors, might also be forming stars, quiet, dark, massive stars made not of fire, but of force. This possibility is both humbling and thrilling. It suggests that we may be surrounded by a cosmos we scarcely understand, filled with entities and energies that challenge our every assumption. It means that exotic matter is not an abstract curiosity. It is a candidate for one of the most profound forms of existence in the universe. If we could peel back the layers of a Q-star, not with hands, of course, but with instruments fine-tuned to the quantum tapestry of reality, we would find no crust, no core, no strata of atoms crushed into exotic forms. There would be no metallic lattice like in white dwarfs, no neutron degeneracy like in neutron stars, and certainly no singularity at the heart like in black holes. Instead, we would be gazing into something altogether different, a smooth, continuous ocean of quantum field, rippling with structure yet utterly alien to anything we'd call matter. The interior of a Q-star defies the traditional model of a star as a set of concentric layers, each with its own composition and thermodynamic properties. This is because a Q-star is not built from particles in the ordinary sense. It is constructed from a scalar field, a field that permeates the entire volume of the object and whose energy density is distributed throughout the star in a gradient, determined not by chemical composition or nuclear processes, but by the solutions to Einstein's field equations coupled with the scalar field's dynamics. Inside a Q-star, there would be no discrete particles bouncing around, no atoms, no plasma, no ionized nuclei trying to escape gravity. There is only the coherent configuration of a field, smooth, stable, and structured. The energy density is highest at the center and decreases toward the outer edge, but this distribution is not due to gravitational stratification in the traditional sense. Rather, it results from the balance between gravitational attraction pulling the field inward and the scalar field's self-interaction and quantum pressure pushing outward. This means that, in a Q-star, the very concept of inside becomes fluid. There are no walls, no phase transitions from core to mantle to crust. Instead, the interior is a continuous solution, a scalar field profile shaped by equations, not elements. It is like a standing wave in a perfectly tuned chamber of spacetime, with its amplitude and energy density varying smoothly with radial distance from the center. At the core of this structure, the scalar field amplitude is at its peak. This region, though not solid or singular, can be thought of as the heart of the Q-star. Here, the quantum field is most intense, and the gravitational curvature of spacetime is strongest. Yet even at this extreme, the field avoids collapse because its pressure, arising from the field's own dynamics and possibly from quantum effects like Heisenberg uncertainty or field coherence, balances gravity perfectly. There is no event horizon, no infinite density, just a region where the field maintains its maximum configuration. As one moves outward from the core, the scalar field gradually drops in amplitude. The energy density decreases accordingly, but never in discrete steps. It is a gradient, a gentle sloping of field values across space. This is unlike neutron stars, where matter becomes increasingly exotic in deeper layers, from neutron superfluids to possible hyperons or quark matter. In a Q-star, nothing changes categorically. Everything flows from a single unifying field, like a perfectly choreographed quantum performance. At the edge of the Q-star, if such a term even applies, the scalar field doesn't simply end. It tapers off, like mist fading into morning air. This is another critical difference. Q-stars have no hard surface. There's no physical boundary one could touch, even theoretically. Instead, the field extends outward, diminishing in strength, until it becomes indistinguishable from the vacuum. This soft edge could make Q-stars nearly invisible in certain wavelengths, or cause them to emit only faint radiation, depending on how they interact with surrounding matter or light. This tapering gives rise to what some theorists refer to as a field halo, a semi-invisible fringe of low-energy scalar field that extends beyond the denser core. In a neutron star, an infalling particle would strike a solid crust. In a Q-star, it would pass through the outer layers of the field, possibly interacting weakly, decelerating gradually, perhaps radiating energy in an unusual way, depending on the particle's nature. This creates opportunities for future observational techniques. Perhaps strange thermal signatures or gravitational echoes might betray this slow decline in field density. Another tantalizing aspect of the interior is that the scalar field may oscillate. In many models, the field configuration inside a Q-star isn't static, but dynamically oscillating with a frequency set by the particle mass or the charge of the field. These oscillations are coherent. Every point in the star pulses in harmony, like a giant, breathing quantum organism. This doesn't mean the star is unstable. Rather, these oscillations may be the very thing that keeps it stable, like a heart rhythm maintaining life. If true, this oscillation could lead to resonance modes that interact with the external universe, perhaps subtly affecting nearby particles, gravitational waves, or even electromagnetic fields. These internal rhythms might produce detectable signals, like a quiet humming beneath the louder noise of cosmic activity. They could also lead to unique signatures in gravitational wave events, where the post-merger behavior of a Q-star would differ slightly, but tellingly, from that of a black hole or neutron star. And then there's the possibility that the scalar field inside the Q-star is not just passive energy, but a repository of quantum information. Because Q-stars are horizonless, they might not suffer the same fate as black holes when it comes to information loss. Information that falls into a Q-star may be absorbed and encoded into subtle changes in the field configuration, retained, in theory, forever. This raises the possibility that the interior of a Q-star is not only smooth and stable, but also informationally rich. Every ripple in the field might tell a story of past interactions, absorbed particles, or gravitational events long forgotten by the outside world. Such a star, then, would be less like a layered onion and more like a perfectly crafted gemstone, unified, coherent, luminous only to those who understand the patterns beneath its surface. It is a place where geometry and energy become indistinguishable, where space-time is molded gently by a field that both resists and yields to gravity. It is a manifestation not of pressure and temperature, but of symmetry and conservation. From the outside, it would be easy to mistake such an object for a black hole. But from the inside, if one could somehow survive the trip, it would be something else entirely, not darkness, not collapse, not singularity, but smooth, unbroken continuity. A field held in place not by force, but by balance. A star made not of burning gas or degenerate particles, but of pure quantum shape. And in that shape, we might glimpse the outlines of something deeper, a universe that builds not only with particles, but with patterns. Not only with matter, but with meaning. Inside a Q-star, the cosmos stages one of its most profound battles, a relentless, intimate duel between the crushing weight of gravity and the subtle, invisible push of quantum fields. This isn't just a conflict of forces, it's a philosophical standoff between two fundamental principles of the universe. Gravity, the architect of structure, insists on collapse. Quantum physics, the guardian of the micro-world, whispers resistance. And where these two titans meet, a Q-star may rise, not as a compromise, but as a silent equilibrium where either fully wins. To understand this battle, we must first appreciate what gravity wants. Gravity is geometric. It is the curvature of space-time caused by energy and mass. In the absence of a counteracting force, gravity pulls relentlessly inward. In stars, this inward pull is resisted first by thermal pressure from fusion reactions, then by degeneracy pressure as matter becomes more compact. But beyond a certain threshold, past the neutron degeneracy limit, even that resistance fails. Gravity would form a black hole, a singularity wrapped in a horizon where even light cannot escape. Unless something else intervenes. That something else, in the case of a Q-star, is the scalar field, a smooth, energy-rich quantum field that does not rely on particles in the traditional sense, but instead on a stable configuration of potential energy distributed across space-time. Unlike the degeneracy pressure in white dwarfs or neutron stars, which arises from fermions resisting being squeezed into the same quantum state, scalar fields are made from bosons, which love to share quantum states. Their repulsion isn't due to exclusion but to field dynamics, self-interactions and wave coherence that generate a counteracting pressure. Imagine a gravitational collapse in progress, matter shrinks, densities skyrocket, space-time begins to warp. In a typical scenario, this proceeds toward black hole formation. But now imagine that, deep in this collapse, conditions trigger a scalar field configuration. The field emerges, perhaps seeded by dark matter, perhaps a leftover from the early universe, and begins to assert itself. As gravity pulls inward, the field compresses, but instead of collapsing, it reacts. Its self-interaction becomes stronger. Its quantum pressure intensifies. The field resists. This resistance is not mechanical. It's not atoms pushing back. It's geometric and dynamic. The scalar field evolves in response to gravity, altering its spatial profile so that the total stress-energy tensor, a measure of pressure and energy influencing curvature, balances the inward pull. It's a dance written in differential equations, Einstein's equations for gravity, coupled with the Klein-Gordon equation for the scalar field. The key to this balance lies in self-interaction. For a scalar field to prevent collapse, it must interact with itself in a very particular way. A free scalar field, one without self-interaction, can't form a stable star. But introduce a potential with the right shape, say a Mexican hat, or a well with quartic terms, and suddenly the field develops the ability to form standing wave-like configurations. These act like pressure. The field resists compression not because it's made of particles, but because its energy configuration does not favor a smaller volume. In this scenario, the gravitational field itself becomes part of the equation. Unlike ordinary stars, where gravity is an external threat to be overcome, in a Q-star, gravity helps shape the very configuration of the field. The scalar field doesn't merely fight gravity, it works with it, settling into a stable form where both are in tensioned harmony. The star becomes a gravitationally bound soliton, a single cohesive object whose shape and structure emerge from this balance. But this balance is not absolute. There are limits. If the mass of the Q-star exceeds a critical value, the field can no longer sustain itself. The inward pull becomes too strong, the field's ability to maintain its configuration breaks down, and the star collapses. This threshold is analogous to the Chandrasekhar limit in white dwarfs, or the Tolman, Oppenheimer, Volkoff limit in neutron stars. Above it, gravity wins, and the Q-star must give way either to a more compact scalar configuration, if one exists, or to a full black hole. The fact that Q-stars could hover just above the neutron star mass limit, without crossing the black hole threshold, makes them tantalizing. It means that nature might produce them as an intermediate stage, or as an endpoint in systems where traditional matter is no longer viable. It also suggests that Q-stars, if they exist, are incredibly sensitive to initial conditions. A slight change in mass, field energy, or self-interaction strength could determine whether they form, collapse, or dissipate. Quantum pressure in this context is a subtle thing. It's not a force per se, but a result of the field's configuration resisting certain changes. It is an emergent phenomenon, a pattern that arises from the rules governing the field's evolution in curved spacetime. You could think of it like tension in a stretched membrane, not caused by individual particles, but by the geometry of the whole. In this tension lies the possibility of long-lived stability. If the configuration remains coherent, if the scalar field holds its charge, maintains its symmetry, and resists perturbation, then the Q-star can endure. It won't shine like a normal star. It may not radiate at all, save for gravitational effects. But it will be there, heavy, dark, compact, and perfectly balanced on the edge between collapse and dispersal. In some ways, Q-stars embody the deepest paradoxes of modern physics. They exist in a regime where quantum mechanics and general relativity both matter, yet we have no unified theory to fully describe that regime. Q-stars are not a solution to this inconsistency, but a manifestation of it. They live in the cracks between two great frameworks, shaped by both but explained by either alone. And perhaps this is what makes them so compelling. They represent a cosmic stalemate, an object that should collapse, but doesn't, because the rules of the universe are more intricate than our binaries allow. They tell us that gravity isn't always the final word, that fields can sculpt structure as surely as fusion or pressure. They whisper that the universe still holds secrets in the form of stars we can't yet see, but that may be out there, perfectly still, balancing forces that span the chasm between the very large and the very small. When we think of compact stars, white dwarfs, neutron stars, and the enigmatic Q-stars, we often picture objects that are extremely dense, but also incredibly small. And that's true to an extent. But Q-stars, in their defiance of normal physics, push the boundaries in more ways than one. One of their most surprising traits is their potential size. Despite being made not of normal matter, but of coherent quantum fields, Q-stars may stretch beyond the dimensions of typical neutron stars, reaching radii of 20 kilometers or even more. In the grand scheme of stars, this may still seem tiny, but in the realm of ultra-dense objects, it's massive, and it's deeply deceptive. To grasp the significance of this, consider that a typical neutron star, the endpoint of stellar collapse just before black hole formation, has a radius of about 10 to 12 kilometers. That's only slightly larger than a city. And yet, it packs more mass than our Sun into that tiny volume. The density is so great that a teaspoon of neutron star matter would weigh billions of tons. These stars are so compact, their surface gravity warps time and light, creating intense gravitational lensing and time dilation effects. Now imagine a Q-star, a hypothetical object possibly made from scalar fields rather than neutrons, with even more mass, but spread out over an even larger radius, say 20 kilometers or more. That's nearly double the size of a neutron star. And yet, it's not any less compact in terms of the gravity it generates. In fact, it could appear nearly identical to a black hole from a distance, so compact that its light-bending effects mimic the boundary of a horizon. But crucially, there is no event horizon. Just a steep well in spacetime, carved not by ordinary matter, but by a quantum field. Why might Q-stars be larger than neutron stars? The answer lies in the nature of the scalar field. Unlike neutrons, which obey the Pauli exclusion principle and stack up densely at the smallest scale possible, scalar fields don't resist compression in the same way. Instead, their distribution is governed by the field's own dynamics, especially its self-interaction potential, and by the gravitational field it's embedded in. In many models, the scalar field that supports a Q-star tends to spread out over a wider radius. Its energy density is highest at the center but declines gradually, not abruptly, leading to a kind of diffuse halo that can stretch far beyond the typical neutron star edge. Because the field can taper smoothly and doesn't require a solid boundary, the outer edges of a Q-star can extend farther into space than we might expect, potentially doubling or tripling the volume of a similarly massive neutron star. This makes Q-stars deceptively large. From afar, they would appear incredibly compact, possibly only slightly larger than their Schwarzschild radius, the radius of a black hole with the same mass. Their gravitational field could curve spacetime so strongly that even light emitted from their surface would be severely redshifted. To an outside observer, they might look almost indistinguishable from a black hole, especially if the star isn't emitting much radiation. But underneath that compact appearance lies a quantum field configuration that extends significantly farther than the neutron matter of a conventional compact star. It's this deceptive nature that makes Q-stars such compelling black hole mimics. While black holes have no physical surface, just a point of no return, Q-stars do have structure. They have mass, radius, and potentially a surface where infalling particles interact, albeit very weakly. Yet their extended size means that phenomena like gravitational redshift or light deflection are nearly as intense as around a black hole. In effect, the size of a Q-star, paradoxically, allows it to maintain this illusion more effectively. The potential size of Q-stars also has important implications for their maximum mass. Because they aren't limited by degeneracy pressure the way neutron stars are, Q-stars can achieve greater radii and hold more mass before succumbing to collapse. Some estimates suggest that Q-stars could reach masses exceeding 2.5 to 3 solar masses, territory typically reserved for black holes. But due to their scalar field structure, they may avoid forming an event horizon even at these extreme masses, as long as the field configuration remains stable. This larger radius also affects how Q-stars would behave in binary systems or merger events. When two neutron stars spiral into each other, they release gravitational waves that encode detailed information about their masses and radii. If Q-stars exist, and if one or both components in such a merger are Q-stars, the resulting waveform could be subtly, but importantly, different. A Q-star with a larger radius could tidally deform differently during in-spiral. Its matter, or rather, its field, could distribute differently. And after the merger, the remnant might oscillate or radiate in non-standard ways. Astronomers using detectors like LIGO and Virgo are now sensitive enough to pick up on such differences. So far, the data fits well with black hole and neutron star models. But the next few years may bring detections with unusual mass-radius relationships, or remnant signatures that don't quite match known expectations. If we observe an object with a mass above the neutron star limit but without signs of a horizon, the explanation may lie in these deceptively large Q-stars. But perhaps the most mind-bending thing about their size is what it means internally. A Q-star's interior isn't layered like an onion. It doesn't have a crust, mantle, or core. Instead, it's a smooth scalar field, tapering gradually from center to edge. A larger radius means a larger volume over which the field configuration can remain coherent, and this may actually improve the object's stability. Larger Q-stars may have more room to balance gravitational pull against quantum field pressure. And as we've seen, if the scalar field has a conserved charge, like a particle number or global symmetry, it can help the configuration remain stable over cosmological timescales. This size also connects to how the object might interact with its environment. A larger surface, or more accurately, a thicker gradient, means that interactions with infalling matter could be spread over a larger region. The star might appear dark, silent, and cold, but any material it absorbs could subtly alter the field configuration. That, in turn, might produce faint radiation or tiny perturbations in gravitational waves, clues, perhaps, to the star's exotic makeup. So we are left with a strange truth. A Q-star might be twice the size of a neutron star, yet harder to detect. It could be bigger, heavier, and more gravitationally extreme, yet lack the screaming electromagnetic emissions we usually associate with compact objects. It's a master of disguise, wearing the mask of a black hole, holding the structure of a star, and built from ingredients we haven't even confirmed exist. And in that paradox, Q-stars challenge the assumptions we make when looking into the dark. Size, it turns out, isn't just a matter of scale, it's a matter of interpretation. And in the quantum shadows of the universe, even something larger than a neutron star can remain completely hidden. In the strange frontier between neutron stars and black holes lies a razor-thin region of spacetime where things get strange, where gravity is powerful enough to warp light, slow time, and squeeze mass into mind-boggling densities, but not quite enough to seal it off from the universe. It's here that Q-stars may reside, massive, dark, and compact enough to imitate black holes, yet still lacking the defining feature that makes black holes so absolute: the event horizon. To truly understand how a Q-star can be smaller than a black hole, yet not be one, we have to revisit the concept of the event horizon itself. In general relativity, when enough mass is compressed into a sufficiently small radius, the curvature of spacetime becomes so extreme that nothing, not even light, can escape. This critical boundary is known as the Schwarzschild radius. For a non-rotating, uncharged object, it depends only on mass. The more massive the object, the larger the radius within which its mass must be compressed to become a black hole. A star whose radius is smaller than this critical boundary will collapse inward, no matter what, inevitably forming a singularity hidden behind an event horizon. But here's the key: this collapse assumes that nothing can halt gravity once the object passes a certain compactness. What makes Q-stars exceptional is that they do resist that final step, but not by becoming less massive or less compact. Instead, they do something exotic. They remain incredibly dense, they bend light almost like a black hole, and yet they avoid forming a horizon altogether. How? The answer lies in the nature of their internal structure and the properties of the scalar field supporting them. Unlike ordinary stars made of atoms or degenerate matter, Q-stars are not built from particles that crumble under gravity's crush. They are constructed from a scalar field, a smooth, coherent configuration of energy that permeates space. This field has self-interacting properties, meaning it can respond dynamically to changes in gravitational curvature. It doesn't just collapse under gravity, it adjusts, reshapes, and stabilizes. This ability to adapt is critical. As the mass of a Q-star increases, gravity tries to compress the scalar field into a smaller region. In an ordinary object, this would lead to catastrophic collapse. But in a Q-star, the field pushes back, not like bricks resisting compression, but more like a tension membrane finding a new equilibrium. The scalar field's self-interaction potential, and the fact that it may carry a conserved global charge, a kind of built-in stabilizing anchor, allows it to resist further compaction. This interaction creates what physicists call a non-singular, horizonless solution. The field configuration evolves into a stable, solitonic form where the inward pull of gravity is exactly balanced by the outward push of the field's energy, density, and pressure. No horizon forms, because the star never becomes compact enough for the escape velocity to exceed the speed of light. Instead, Spacetime curves sharply, but not infinitely. The escape velocity from the surface of a Q-star may approach 99.999% the speed of light, but it never crosses the threshold. Light emitted from the surface would be so redshifted it would appear almost invisible to distant observers, making the Q-star look eerily like a black hole. Yet crucially, it is still visible in principle. If you sent a signal toward it, it wouldn't vanish forever. If you tossed an object toward its surface, the object wouldn't be lost beyond the veil of no return. It would encounter a real, physical structure. This difference has enormous implications. Because Q-stars lack event horizons, they do not suffer from the same theoretical paradoxes as black holes, chief among them, the information paradox. In black holes, information about matter that falls in is thought to be lost beyond recovery, raising questions about how that squares with the laws of quantum mechanics. But in a Q-star, information may still reside in the scalar field structure. It may be distorted, scrambled, and encoded in bizarre ways, but it is not lost. This could make Q-stars an appealing alternative to black holes in a universe where quantum mechanics and general relativity must one day be reconciled. Another striking implication is related to Hawking radiation. Black holes, according to quantum theory, slowly evaporate by emitting thermal radiation. But since this process is governed by the properties of the event horizon, Q-stars, lacking such a horizon, may not radiate in this way at all. They may be truly stable, long-lived objects, persisting for billions or even trillions of years without decay. But perhaps the most visually deceptive feature of a Q-star is how closely it resembles a black hole from the outside. If one were to orbit a Q-star at a safe distance, you'd experience all the same gravitational effects you would near a black hole: time dilation, orbital precession, redshifted light. The star would bend light so severely that it might cast a photon sphere, a ring of light similar to what we see in the Event Horizon Telescope's image of M87. Yet, unlike a black hole, there would be no actual horizon beneath that ring, just a very steep gravitational gradient. This extreme similarity has led some physicists to suggest that some of the objects we currently think are black holes might actually be Q-stars. After all, we've never observed an event horizon directly. We infer its presence by the absence of surface emissions, by the behavior of matter around it, and by the object's mass-to-radius ratio. If a Q-star can mimic all these traits, then the difference between the two might be hidden in the shadows of our observational limits. The final escape from becoming a black hole hinges on how the field behaves as mass increases. In many models, Q-stars have a maximum mass limit. If you try to add too much mass, the scalar field can no longer balance gravity, and the object collapses into a black hole anyway. But until that threshold is crossed, the Q-star continues to exist as a hypercompact, horizonless body, darker than a neutron star, but not quite swallowed by the black hole's abyss. And this, not quite, makes all the difference. It's a narrow line, perhaps only fractions of a kilometer between horizon formation and scalar field stability. But within that window lies an entirely different kind of cosmic object. One that bends the rules without breaking them. One that holds together not by pressure, but by balance. One that shows us that gravity alone does not determine fate, that quantum fields, given the right conditions, can push back against the most overwhelming force in the universe. Q-stars are smaller than black holes, in the sense that they occupy that subhorizon region without forming an event horizon. Yet they are, paradoxically, also more complete. They have structure, identity, internal dynamics, and perhaps even memory. They are what black holes might have been if gravity were not the sole arbiter of stellar destiny. And in this slender space, just before the horizon, just short of singularity, Q-stars quietly defy the universe's most absolute boundary, standing as monuments not to collapse, but to balance. One of the most enigmatic ideas in the physics of black holes is the no-hair theorem, an elegant but austere concept that states black holes are remarkably simple objects. According to this theorem, a black hole, no matter how it forms, can be completely described by just three observable quantities: its mass, its electric charge, and its angular momentum. Everything else, the identity of the collapsing matter, the structure it once had, even the information it carried, is lost behind the event horizon. The resulting object is bald, featureless, and indistinct. Hence the poetic phrase, "Black holes have no hair." But Q-stars? They might just grow some. Unlike black holes, which strip away the intricate details of their progenitor systems, Q-stars offer a radically different possibility, that compact, massive, dark objects can still retain internal structure and memory, visible or at least theoretically recoverable from the outside world. In doing so, they challenge not just the simplicity of black holes, but the very nature of what it means to collapse under gravity. The no-hair theorem is a consequence of general relativity's powerful constraints. It arises from the idea that once matter collapses into a black hole and crosses the event horizon, its internal complexity becomes causally disconnected from the rest of the universe. No information can escape, no structure remains accessible. Black holes are solutions to Einstein's equations with a minimum of variables. They smooth over everything else. But Q-stars do not possess an event horizon. They never cross that fatal boundary. This one fact opens the door to a completely different regime of physics. Because Q-stars are held up by scalar fields, fields that may carry conserved quantum charges, have complex internal configurations, and respond to gravity dynamically, they do not need to simplify themselves the way black holes do. They can, in theory, preserve the identity of the field configuration that defines them. This means that a Q-star, far from being bald and featureless, might be a rich and textured object, defined not only by its mass and spin, but by the exact nature of its scalar field, its charge distribution, its frequency of oscillation, the shape of its self-interaction potential, and the way those factors influence its gravitational field. For example, if the scalar field that composes a Q-star has a conserved global charge, say, a quantum number like particle number or a hidden symmetry charge, then the star retains that charge across its evolution. It doesn't fade into anonymity. That charge affects how the field behaves, how the star reacts to external perturbations, and how it might be distinguishable from other Q-stars with similar mass and spin but different field parameters. In essence, Q-stars can have hair, quantum, hair, field, hair, informational, hair, all the nuanced traits that black holes are said to lack. And there's more. Because Q-stars may not be perfectly static objects but rather oscillating field configurations, they might also have time-varying properties, internal pulsations or rotational dynamics that are not simply averaged out or hidden by an event horizon. These oscillations could, in principle, influence how the star emits gravitational waves, how it interacts with nearby matter, or how it perturbs the surrounding spacetime. A black hole remains quiet once it forms. A Q-star may hum with subtle complexity. This challenges not just the classical no-hair theorem, but also its extensions in quantum gravity and field theory. Some theorists have suggested that black holes might have soft hair, after all, minute quantum features imprinted on their event horizons. But these suggestions remain highly speculative and difficult to test. Q-stars, on the other hand, could provide a concrete alternative, an ultra-compact object that retains complexity not in whispers on a horizon, but in the very bulk of its structure. In practice, this could mean that Q-stars exhibit unique gravitational signatures. Their gravitational waveforms during in-spiral or merger events could differ subtly from those of black holes. These differences wouldn't just arise from mass or spin, but from the internal configuration of the scalar field, how it reacts to tidal forces, how it deforms under stress, how it rings after a collision. Each Q-star could, in theory, have its own unique signature, its own voice, in the gravitational wave spectrum. Another implication concerns information recovery. One of the deepest paradoxes in theoretical physics is the idea that black holes destroy information, a conflict between general relativity and quantum mechanics. If Q-stars exist, they may offer an elegant loophole. Since there's no event horizon, no information is permanently lost. Data about infalling matter could be absorbed into the field structure, encoded in the configuration of the scalar field, and, even if extremely difficult, potentially recoverable. The Q-star becomes not a vault with no door, but a vault with a lock we don't yet know how to pick. There's also the question of evolution and uniqueness. In black hole physics, the no-hair theorem implies that different initial conditions often lead to the same end state. Two completely different types of stellar collapse, say, one from a neutron star and one from an exotic dark matter object, could result in identical black holes. But in Q-star models, the story could be very different. A scalar field collapse might settle into a configuration that reflects its initial properties, its symmetry, its charge, its energy distribution. That means two Q-stars of the same mass and radius might still be quantitatively distinct, each carrying the fingerprint of its origin. And this opens yet another possibility, that Q-stars may come in varieties. Not a single type of object, but a whole family of compact stars, each defined by different scalar fields, different interaction terms, or different conserved charges. They might range from minimally charged, nearly featureless configurations to highly structured, dynamic stars with rich internal geometry. Their hair would be their diversity. From a philosophical perspective, this is deeply profound. Where black holes are the great erasers of cosmic identity, Q-stars become the keepers of cosmic memory. They represent a vision of the universe where complexity isn't doomed to collapse, but can survive in the most extreme conditions imaginable. A Q-star is not a gravitational dead end, it is a quantum monument, shaped not only by mass and spin, but by the invisible architecture of fields and charges. This doesn't mean Q-stars violate the laws of physics. On the contrary, they may be fully allowed by the union of general relativity and quantum field theory. But they do force us to reconsider assumptions that have guided black hole theory for decades. They suggest that nature might offer alternatives to the absolute finality of event horizons. That gravity and quantum mechanics can form not only paradoxes, but possibilities. So while black holes may remain bald in the classical picture, Q-stars offer a new narrative, that perhaps some stars wear their history like a crown, not hidden, but woven into their very being. If we could gaze across the cold vastness of space and spot a Q-star, what would we actually see? What would such a strange and exotic object look like, and how would it differ from the more familiar compact cosmic actors, neutron stars and black holes? The answer is fascinating, if frustrating, because a Q-star might look like nothing at all. Or rather, it might look like everything else, while being something entirely different underneath. To begin with, Q-stars are expected to be incredibly dark. Unlike ordinary stars, they do not shine with the light of fusion. They have no burning core, no corona, no surface from which photons escape freely in great quantities. They are not furnaces. They are fortresses of gravity and field dynamics. Their darkness, however, is not total. They are not voids like black holes. They don't swallow light unconditionally. Instead, they may emit some form of radiation, albeit very faint, redshifted, and difficult to detect. The exact nature of that radiation would depend heavily on the type of scalar field composing the Q-star. In many theoretical models, Q-stars emit minimal electromagnetic radiation, particularly if the scalar field doesn't interact with electromagnetism directly. In such cases, the Q-star could appear almost entirely invisible to telescopes that rely on light. However, if the scalar field has even the slightest coupling to normal matter or to photons, the star could produce exotic emission signatures, perhaps bursts of high-energy particles, pulses of gamma rays, or strange spectral lines that don't match any known atomic transitions. This is where things get intriguing. Imagine scanning the sky and coming across an object with the mass of several suns, tightly packed into a volume only a few dozen kilometers wide, bending spacetime like a black hole, yet not emitting the expected Hawking radiation or black hole accretion disk signals. No jets. No flickering X-ray corona. Just a dark mass that subtly distorts the paths of stars and light around it. It might seem invisible, but under the right conditions, it could appear as a quiet void with a whisper of light, detectable only through its gravitational footprint. Gravitational lensing offers one of the most promising visual clues. Like black holes and neutron stars, Q-stars warp spacetime strongly enough to bend passing light. A background star passing behind a Q-star might be momentarily magnified, distorted into a ring, or even duplicated, effects known as Einstein rings and gravitational mirages. But unlike a black hole, a Q-star might allow some light to escape from its near-surface region. That light would be extremely redshifted, appearing in infrared or radio wavelengths, and likely very weak. Yet it would be there, evidence of a surface, or at least of matter or fields interacting near the core. This would be the Q-star's optical fingerprint, a gravitational lens almost indistinguishable from a black hole's, but with faint surface emissions that reveal a crucial difference. The object wouldn't swallow all light permanently. Some photons, barely, could escape. And in their fading spectrum, we might read the tale of the scalar field within. Depending on its age and environment, a Q-star might also exhibit unusual variability. If the scalar field inside is oscillating, as some models suggest, the star could emit pulse radiation in a very specific frequency, like a heartbeat in the cosmic background. This might be detectable in radio or gravitational wave bands as rhythmic, steady pulses, somewhat akin to a pulsar, but with distinctly non-atomic timing characteristics. No neutron cross-spinning at regular intervals. Just the resonance of a quantum field contained by its own structure. And speaking of pulsars, one of the more fascinating possibilities is that some known pulsars might already be Q-stars in disguise. The rhythmic radio pulses we observe from these objects are generally attributed to rotating neutron stars with strong magnetic fields. But what if some of those signals come from rotating Q-stars with scalar field-induced oscillations or strange magnetofield interactions? Their appearance would be nearly identical from afar, but inside they'd be built from something entirely different. In terms of appearance in space imagery, Q-stars would likely be compact, dark, and eerily quiet. They wouldn't flare or flare out unless perturbed. They'd sit in space like invisible anchors, massive, powerful, but largely inert to the senses. If they reside in binary systems and accrete matter from a companion star, they might briefly show signs of activity, perhaps emitting high-energy flares or exhibiting non-thermal radiation due to interactions at their edge. But even then, the pattern of emissions might differ from that of black holes or neutron stars, lacking the telltale broad X-ray spectrum of a hot accretion disk. In high-resolution simulations or future imaging, a Q-star might resemble a dim, sharply defined gravitational silhouette, a round, blackish blot against the stars with a thin corona of warped light curling around it. It might have a photon sphere, a ring of trapped light circling near its radius, producing a halo similar to what we've seen around M87. But there would be subtle differences. The ring would be slightly brighter on one side, slightly thinner, and possibly exhibit polarization properties that betray the lack of an event horizon. Another possibility is that Q-stars might glow faintly in gravitational radiation. If they oscillate, merge, or interact with other compact objects, they would produce gravitational waves just like black holes, but with a twist. Their post-merger signatures might differ slightly in waveform, ring-down frequency, or damping rate. This gravitational fingerprint could be used to identify them, even if no photons reach our detectors. In that sense, Q-stars might look less like traditional stars and more like ripples in the fabric of reality itself, visible not to the eye, but to the space-time detectors like LIGO and Virgo. Ultimately, Q-stars might not look like much, just points of intense gravity, radiating faintly if at all, blending into the backdrop of the cosmos. But their subtle differences, the ghost light escaping from beneath what should be a horizon, the odd rhythms of scalar fields, the mass-to-radius ratio that defies conventional categorization, would mark them as something new. And in a universe ruled by light, perhaps it is the objects that defy brightness, that hide their brilliance in warped fields and soft gravitational murmurs, that reveal the next chapter of cosmic understanding. Q-stars are not stars of fire and fusion. They are stars of balance, structure, and subtlety, objects that shine not with light, but with possibility. Detecting a Q-star is one of the great modern challenges in observational astrophysics. These elusive objects occupy a strange middle ground in the cosmic zoo, neither neutron stars nor black holes, but something eerily similar to both. They are quiet, compact, and gravitationally potent, yet unlike black holes, they have no event horizon. Unlike neutron stars, They may not emit strong electromagnetic radiation or have a crust of particles spinning down over time. So how could we ever tell one apart from the others? The answer lies in two of the universe's most subtle messengers: gravitational waves and precise timing measurements. These tools don't just look for light. They look for changes in time, in space-time, in rhythm. They reveal not what the object looks like, but what it is. Let's begin with gravitational waves, the ripples in space-time caused by massive objects accelerating. These waves carry with them imprints of the dynamics that created them: mass, distance, spin, shape, and most importantly, how those properties change during an interaction. When neutron stars or black holes collide, they produce a characteristic gravitational wave signal. From this, scientists can determine their properties with stunning accuracy. But what if one of those objects isn't quite what it seems? If a Q-star participates in such a collision, its gravitational wave signature may differ ever so slightly from that of a black hole or a neutron star. First, the tidal deformability, a measure of how easily an object is distorted by its companion's gravity, is different for Q-stars. Neutron stars, being made of normal matter, are relatively squishy compared to black holes. Black holes are infinitely stiff; they cannot be deformed at all. Q-stars, composed of scalar fields, lie somewhere in between. They deform, but not like matter-bound objects. Their field configuration stretches differently under tidal forces, leaving a distinct pattern in the gravitational waveform during the inspiral phase of a binary merger. This means that by carefully analyzing the gravitational wave signal from a merger, researchers could infer whether the objects involved had the right deformability for a neutron star, or something strange. If one component appears too compact to be a neutron star but too deformable to be a black hole, it could very well be a Q-star. The ring-down phase, the moment after a merger when the final object settles into its new shape, is another critical window. Black holes ring down in predictable ways, producing damped oscillations known as quasi-normal modes. These modes depend only on the black hole's mass and spin. But Q-stars, being structured objects, could exhibit additional or shifted oscillation modes due to the internal behavior of the scalar field. These differences in frequency and damping might leave subtle but telltale signs in the gravitational wave data. Next, consider precise timing, especially from pulsar-like signals. Some Q-stars, particularly if rotating, might mimic pulsars, neutron stars that emit regular beams of radio waves. These beams sweep across Earth with clock-like precision. But Q-stars, due to their smooth scalar field interiors, wouldn't have a rigid crust or typical magnetic poles. If they emit at all, their emission would likely be governed by scalar field dynamics or non-standard magnetic processes. This could cause them to show timing irregularities, subtle drifts, frequency modulations, or even oscillatory behaviors that deviate from standard pulsar models. For instance, a Q-star pulsar might emit with incredible regularity for a time, then suddenly glitch, in a way inconsistent with crustal cracking, a known neutron star behavior, suggesting a different internal mechanism. In extreme environments, like binary systems or accretion disks, Q-stars might exhibit quasi-periodic oscillations, QPOs, in their emitted signals, similar to neutron stars. But the frequencies of these QPOs are often linked to the internal structure and the radius of the star. A Q-star, having a different equation of state than neutron stars, could produce QPOs with anomalous frequencies. These deviations could act like fingerprints, signaling a non-standard compact object. Another powerful method for detection lies in mass and radius measurements. If astronomers observe an object with a well-defined radius that's too small for a neutron star but clearly lacks a black hole's event horizon, a Q-star becomes a strong candidate. The challenge here is that such measurements require incredibly precise data, often from X-ray bursts, binary orbital dynamics, or lensing effects. Objects with mass above the neutron star limit, roughly 2.5 solar masses, but lacking signs of a black hole's horizon, fall into a tantalizing gray area. If their compactness, mass-to-radius ratio, is extremely high but not total, and they still emit faint radiation, then they almost certainly cannot be conventional stars or black holes. This observational void is where Q-stars might reside, silently waiting for instruments like NICER, Neutron's Star Interior Composition Explorer, or next-generation gravitational wave detectors like LISA and the Einstein telescope to find them. Further, black hole candidates in X-ray binaries are often inferred rather than confirmed. If future observations reveal surface interactions, delayed light echoes, or anomalies in the infall patterns of matter, such as matter bouncing off a surface instead of vanishing into an event horizon, it might suggest the presence of a horizonless compact object. Q-stars would be a natural fit. Finally, consider multi-messenger astronomy, the simultaneous detection of gravitational waves and electromagnetic signals. If a merger produces strong gravitational waves consistent with a high-mass compact object, but lacks the expected X-ray or gamma-ray afterglow, or if the signal fades too slowly or shows unusual echoes, it could point to an object without an event horizon. That mismatch would be exactly the kind of signature that suggests a Q-star. In summary, detecting a Q-star will likely depend not on a single glowing observation, but on a mismatch between predictions and reality, between what general relativity expects and what nature delivers. A slight inconsistency in a waveform, a strange timing signal, a redshifted photon escaping where none should, or a gravitational ring-down that doesn't quite match known templates. These anomalies, once thought to be noise or outliers, might instead be whispers from the quantum stars hiding in plain sight. Q-stars will not announce themselves with brilliant flares or loud gravitational crashes. But they might, in the soft static of the cosmos, leave just enough of a trace for us to notice. And when we do, our understanding of what stars can be, and what matter itself can become, will be forever transformed. If Q-stars are indeed held together by exotic scalar fields, then one intriguing question naturally arises: what happens to the scalar field outside the star's core? Does it abruptly end at the Q-star's edge like the surface of a neutron star? Or does it fade more gently into the surrounding spacetime, extending outward like a mist of invisible energy? According to several theoretical models, the answer may point toward a subtle yet powerful phenomenon, a quantum field halo, an extended region around the Q-star where the scalar field still persists, though in a diluted and diffuse form. To understand this, let's first revisit how scalar fields function in these theoretical objects. Inside the Q-star, the scalar field is typically in a coherent configuration, a compact, high-density region where its energy is concentrated. This interior behaves much like a soliton, a stable wave-like structure that maintains its shape due to a balance between field pressure and gravitational attraction. But scalar fields, especially those with long-range interactions or minimal coupling to ordinary matter, do not necessarily drop to zero at the boundary of the star. Instead, they may gradually decrease in intensity as you move away from the core, forming what physicists call a tail or halo, a region of spacetime where the scalar field still exists, albeit very faintly. This halo is not composed of matter in any traditional sense. There are no atoms, no electrons, no ions. It's a pure field configuration, a ghostly scaffold of energy that subtly influences the curvature of spacetime. It may extend many kilometers, or even thousands of kilometers, beyond the star's visible or gravitational boundary. And while this quantum field halo might be invisible to telescopes, it could leave detectable traces in precise astrophysical measurements. One of the most direct consequences of such a halo is its impact on orbital motion. If a Q-star possesses a surrounding scalar field that slightly modifies the gravitational potential outside the star, then objects orbiting it, such as gas particles, companion stars, or even hypothetical spacecraft, would experience a gravitational field that doesn't quite match Newtonian predictions. This could manifest as tiny deviations in orbital precession, timing delays in binary systems, or discrepancies in accretion disk behavior. While these effects might be small, they could become noticeable with high-precision instruments, especially in systems where we can measure orbits down to milliseconds of accuracy. Another potential signature is photon propagation. If light passes through or near a Q-star's scalar halo, the field could induce minuscule changes in the path of the light, either through gravitational lensing or through subtle quantum interactions, if the scalar field couples to photons. This might result in frequency shifts, delays, or even exotic polarization effects that distinguish Q-stars from black holes or neutron stars. In extreme cases, the halo might act like a weak gravitational lens all by itself, creating faint distortions in the light from background objects. Perhaps even more exotic is the idea that the scalar field in the halo could interact with itself or with dark matter in unexpected ways. If the field has nonlinear self-interactions, as many scalar field models predict, then the halo might not be a simple, passive gradient. It could be structured, with standing waves, oscillatory nodes, or slowly rotating features. These structures might subtly affect how nearby matter behaves, possibly even creating quasi-stable shells of field density outside the core. In a sense, the Q-star wouldn't be just a single compact object, but a field-dressed body, wrapped in layers of fluctuating, almost ethereal energy. In some models, this halo could carry quantum numbers, like conserved global charge, that are not confined strictly to the interior of the star. The total charge of the Q-star might not be compactly located at its center but instead spread over a region extending well beyond the surface. This would mean that interactions with the object, such as accretion or decay, could involve not just contact with the core, but with the extended field itself. A particle passing through the halo might undergo interactions that subtly alter its trajectory or energy, depending on the properties of the field. Furthermore, scalar field halos could provide a partial explanation for some of the mysterious, dark mass signatures we've observed in certain astrophysical systems. If a Q-star sits at the center of a dark halo, and that halo is gravitationally active but electromagnetically invisible, it could contribute to the galaxy's mass profile in a way that mimics dark matter. Some astrophysicists have speculated that extended scalar field configurations, possibly left over from the early universe, could cluster in galaxies, forming bosonic fogs, or scalar clouds, around massive objects. Q-stars, as compact field objects, could serve as seeds for these larger-scale field structures. Detecting such halos would be a monumental challenge. They would not shine. They would not radiate in conventional ways. But if we could map the gravitational potential around Q-stars with extreme precision, perhaps through the motion of pulsar companions or the bending of light from distant quasars, we might begin to detect small anomalies, signals that hint at something more than just a point mass. Something extended. Something structured. Something field-like. There's also the tantalizing possibility that scalar halos might oscillate. Unlike a static mass shell, a quantum field halo could support time-dependent behaviors, waves or pulses traveling through the field, perhaps even responding to tidal interactions or cosmic background perturbations. These could emit gravitational waves on their own, at very low amplitudes, adding an ultra-quiet but persistent hum to the gravitational landscape around the star. In essence, a quantum field halo would be the ghost of the Q-star, extending its presence beyond what mass and light alone would suggest. It would give the star a kind of quantum aura, a veil of subtle influence that blurs the boundary between star and space, between object and field. And in doing so, it would offer not only a new way to detect Q-stars, but a new vision of what a star can be, a central locus of condensed energy, yes, but also the heart of a living field that breathes into the fabric of the cosmos. We're not just looking for light anymore. We're listening for distortions in time, scanning for nudges in orbit, hunting for tremors in gravitational silence. And somewhere, in those quiet folds of reality, a Q-star's halo might already be waving. In the grand theater of the cosmos, nearly every celestial body we know is constructed from the same fundamental ingredients: atoms, particles, nuclei. Whether it's a shining main sequence star like our Sun, or the dense, rapidly spinning corpse of a neutron star, the material of the universe has always seemed to boil down to matter. But Q-stars challenge that notion in the most radical way imaginable. They aren't made of atoms. They aren't composed of protons or neutrons, or even electrons. A Q-star is something altogether different, a star made of force, a self-sustaining configuration of pure energy, shaped and sustained by the rules of quantum fields and gravity. To appreciate just how alien this is, we need to understand the difference between matter-based stars and field-based stars. In matter-based stars, white dwarfs, neutron stars, or even black holes, the internal support against gravity comes from physical particles resisting compression. In white dwarfs, it's electron degeneracy pressure. In neutron stars, it's neutron degeneracy and nuclear forces. These are tangible pressures, quantum mechanical effects of tightly packed particles refusing to share the same state. As the mass of the object increases, the particles become increasingly squeezed until a limit is reached, and gravity wins. This is the road that leads ultimately to a black hole, where matter is crushed beyond all known resistance. But Q-stars offer a detour on that road. They don't rely on particles pushing back. Instead, they are held up by the self-organization of a field, a smooth, continuous distribution of energy known as a scalar field. This field isn't a collection of particles in the traditional sense. It's more like a shimmering, invisible fabric stretched across space-time, with its own dynamics, rules, and internal coherence. The field permeates the Q-star's interior, and possibly even extends beyond it in the form of a halo, as we've explored, forming a stable configuration where gravity and field pressure remain in perfect tension. What keeps the Q-star from collapsing? Not atomic bonds, not thermal pressure, not even degeneracy. It's the potential energy of the scalar field, finely balanced against the pull of gravity. This field may oscillate in place, creating a standing wave of energy, or it may adopt a static, soliton-like profile, a self-sustained lump of field energy that resists compression due to its own internal structure. In some theories, the field carries a conserved quantity such as a nodal charge, a kind of built-in symmetry that grants stability and prevents decay. The star exists not because of what it contains, but because of the way the field is arranged. This means a Q-star is, quite literally, an object made of a force. It's not a container of matter, but a configuration of the very rules that govern force interactions, specifically, a scalar interaction that might be connected to fundamental fields we don't yet fully understand. It's a bit like a vortex in water, not a thing made of water drops, but a shape in the water, a pattern that persists because of the motion and forces within the medium. Imagine, then, a Q-star as a gravitationally bound pattern, an eddy of the universe's quantum fabric, compressed by its own mass but held aloft by the tension and structure of a self-regulating field. No particles sit on its surface. No atoms form lattices inside. There is no crust, no core, no layered structure of heavier and heavier elements. Instead, there is only the smooth, invisible whisper of energy, distributed according to a complex mathematical function, spread across a region of extreme curvature in space-time. The field may be incredibly dense near the center, tapering off gradually toward the edges. At its peak, the energy density could rival, or even exceed that of a neutron star's core. But there is no singularity, no discontinuity, only a perfectly smooth drop-off, like a fading ripple in still water. The gravitational field generated by this structure would be immense, but because the object lacks an event horizon, it is still connected to the rest of the universe. Information may enter and perhaps subtly escape, something impossible in traditional black holes. What's even more striking is that this field-based composition may give the Q-star quantum properties on a macroscopic scale. While normal stars are classical objects, huge systems of particles obeying collective behavior, Q-stars may behave, at least partially, as giant quantum systems. Their stability, their interactions, their internal coherence may all be governed not just by gravity, but by the laws of quantum field theory. That opens the door to entirely new types of behavior: macroscopic quantum oscillations, field-induced rotations, non-local interactions, and perhaps even quantum entanglement effects with other scalar field configurations in distant regions of space. Think about the implications of this. A Q-star isn't a burning furnace. It doesn't shine. It doesn't churn with convection or fuse elements into heavier ones. It just is, a timeless configuration, stable across millennia, barely interacting with the universe around it unless disturbed. It is not matter in the conventional sense. It is organized force, given form by the very laws that govern existence, shaped into a gravitational entity through balance alone. It may sound poetic, but this is no fantasy. It's a consequence of well-understood physics extended into unexplored regimes. Scalar fields are already central to many cosmological theories. Dark energy, inflaton fields, and the Higgs mechanism are all built upon scalar dynamics. If such fields exist universally, then under the right conditions, they might concentrate into gravitational objects. In that sense, Q-stars would not be bizarre exceptions. They would be natural products of the universe's deep architecture. And here's a final mind-bending thought. Because scalar fields may not interact strongly with ordinary matter, Q-stars could be utterly invisible to most observational techniques. They wouldn't reflect light, absorb it in normal ways, or generate familiar spectra. They would just sit there, dark knots of energy, woven into the fabric of reality, detectable only through their mass, their gravity, and the tiny anomalies they create in the rhythms of space-time. To spot one would be to glimpse force turned to form, energy turned to structure, laws turned to objects. A Q-star is not just a star that defies collapse. It's a cosmic equation given shape, a star that exists because the rules say it can, and because nothing yet has said it must collapse. In the end, when we speak of a Q-star as a star made of force, we're not being metaphorical. We mean it literally. These are stars without matter, without flame, without fusion, stars that emerge not from what the universe contains, but from what it allows. The question of stability is the knife edge on which the entire concept of Q-stars balances. Are they truly stable, long-lived entities capable of persisting for billions of years like conventional stars? Or are they merely transitional phenomena, short-lived quantum configurations on their inevitable march toward black hole collapse? The answer isn't yet certain. But what's clear is that the stability of Q-stars touches on some of the deepest and most unsettled issues in modern physics, from quantum field dynamics to the very geometry of spacetime itself. At the heart of the stability question is this: gravity wants to pull everything inward, collapsing mass into the smallest possible volume. The more compact the object, the stronger its self-gravity becomes. For normal stars, this gravitational pull is counteracted by pressure, thermal pressure in main sequence stars, degeneracy pressure in white dwarfs and neutron stars. But even these pressures break down at extreme densities, leading ultimately to black holes. Q-stars, however, propose a different kind of resistance, one provided not by matter, but by the configuration and dynamics of a scalar field. So the real question becomes, can a scalar field configuration permanently resist gravity? Theoretical studies suggest that, under certain conditions, the answer is yes. Scalar fields can form solitonic solutions, coherent, non-dispersing structures that resist decay. In flat spacetime, these structures are well understood in the context of field theory. When gravity is added to the equation, the challenge increases, but still, under the right potentials and boundary conditions, stable equilibrium configurations have been found in simulations. These solutions show that scalar fields, particularly those with self-interaction terms, nonlinear potentials, can reach a kind of minimum energy state where gravitational pull is perfectly counterbalanced by field dynamics. Such solutions are what define a stable Q-star. The field is compressed just enough to generate the gravitational potential that holds it together, but not so much that it triggers collapse. The structure isn't explosive or chaotic, it's smooth, symmetric, and finely tuned. Like a tightrope walker suspended between two abysses, the Q-star lives on a razor-thin balance between space-time curvature and quantum repulsion. However, this balance can be fragile. It depends critically on the mass and energy density of the field. If too little energy is present, the structure cannot form a compact star at all, it simply disperses into the vacuum. But if too much mass is accumulated, gravity overwhelms the field's ability to hold its shape. The configuration becomes unstable and may collapse into a black hole. This leads to the idea of a critical mass limit for Q-stars, a value above which the field cannot maintain equilibrium. Much like the Tolman, Oppenheimer, Volkoff limit for neutron stars, Q-stars may also have a threshold beyond which stability becomes impossible. What happens near that limit is where things get speculative. Does the Q-star collapse instantly into a black hole? Or does it pass through intermediate phases, shedding energy in bursts before giving in? Could some configurations hover on the brink indefinitely, appearing almost stable while being subtly unstable, decaying only after vast timescales? These questions are active areas of research in quantum gravity and numerical relativity. Some studies suggest the existence of metastable Q-star states, structures that are not eternally stable, but can persist for extremely long periods before collapsing. These would be similar to false vacua in quantum field theory, temporarily stable but ultimately doomed. Such Q-stars might arise naturally in astrophysical environments, perhaps formed in the collapse of massive stars, and then exist for millions or billions of years before tipping over into black hole formation. There would be the quantum echo of stellar death, a fleeting pause in the great gravitational story. There's also the question of external disturbances. A Q-star might be stable in isolation, but what happens if it accretes matter? If even a small amount of additional mass pushes it past its stability threshold, the entire configuration could destabilize. In this sense, Q-stars could be conditionally stable, robust in a vacuum, but vulnerable in dynamic environments. A companion star, a stream of interstellar gas, or even a close flyby of another compact object could provide the nudge that ends its delicate balance. Another concern is quantum decay. Even if classically stable, Q-stars might not be immune to quantum tunneling or decay through particle emission. If the scalar field has an associated vacuum state, the configuration could potentially decay into a lower energy state, releasing energy and collapsing in the process. These decay processes would be rare and probabilistic, but over cosmological timescales, they might play a significant role. The stability of the Q-star might then become a question not of if it will collapse, but when. Yet despite all these caveats, there are solid theoretical reasons to believe that at least some Q-stars could be fully stable, enduring objects. If the scalar field has the right properties, sufficient self-interaction, conserved global charges, and appropriate boundary conditions, it could resist collapse indefinitely. These stars would be as permanent as neutron stars, perhaps even more so, given the absence of particle interactions and crustal instabilities. In fact, some versions of Q-stars might even be more resistant to decay than neutron stars, precisely because they lack the conventional matter structure that leads to crust quakes, magnetic decay, or fusion instability. And this is where the profound implications lie. If Q-stars can be stable, if force, not matter, can organize itself into a star that endures, then the universe may be home to a vast population of such objects, invisible to our current instruments, quietly resisting collapse in the depths of space. Some may have formed in the early universe, surviving to this day. Others may arise from the collapse of neutron stars or strange matter. Their presence would rewrite our understanding of stellar evolution, gravity, and the quantum nature of the cosmos. But until we observe one, we must live with uncertainty. Are Q-stars real? Are they stable? Are they long-term fixtures of the universe or brief apparitions flickering into black holes? The theories are tantalizing. The equations allow for them. The physics does not rule them out. And if they exist, they might be the most graceful balancing act in the universe, a star not born of matter, but of energy poised on the edge of gravity. Where exactly does a Q-star cease to be a star and begin its transformation into a black hole? This is perhaps one of the most profound and unsettled questions in theoretical astrophysics today. The line between stability and collapse, between a horizonless quantum configuration and an event horizon-cloaked singularity, is not just thin, it may be blurred, conditional, and defined by physics we don't yet fully understand. For traditional compact objects, we have fairly well-defined mass thresholds. White dwarfs, for instance, are limited by the Chandrasekhar limit. About 1.4 times the mass of the Sun. Neutron stars are constrained by the Tolman, Oppenheimer, Volkoff, TOV limit, somewhere around 2 to 2.5 solar masses, depending on the equation of state. Beyond that, the degeneracy pressure that resists gravitational collapse gives way, and a black hole is the inevitable outcome. But Q-stars don't play by those rules. Their resistance to gravity doesn't stem from particle degeneracy pressure. It arises from the configuration and energy of a scalar field, a field that is smooth, coherent, and often nonlinearly self-interacting. That means the collapse threshold for a Q-star isn't set by how densely particles can pack together, but by how much scalar field energy can be contained within a compact region of spacetime before gravity overwhelms the structure. This is where things get especially intriguing and frustrating. Because the scalar field can have a wide variety of potentials and coupling constants, there's no single universal mass limit for Q-stars. The collapse threshold depends heavily on the specific properties of the field. How strong is the field's self-interaction? Is it minimally or non-minimally coupled to gravity? Does it carry a conserved charge or quantum number? Is the field real or complex? Is the configuration spherically symmetric or rotating? Each of these factors changes the mass-radius relation for the Q-star. For some configurations, the maximum mass may only be slightly above that of neutron stars, say, 2.5 to 3 solar masses. But for other field structures, especially those involving rotating or charged scalar fields, that limit could climb much higher, perhaps even reaching 10 solar masses or more, without forming a black hole. In numerical simulations of scalar field stars, like Boson stars, which are closely related to Q-stars, a typical behavior emerges. As mass increases, the star becomes more compact, and the field energy gets more tightly bound. Eventually, a peak is reached in the mass-radius curve, the maximum mass for that specific field configuration. Beyond that point, no stable equilibrium exists. If more mass is added, or if energy is perturbed, the object becomes dynamically unstable and collapses to a black hole. What makes this situation even more subtle is that, in many cases, the transition from Q-star to black hole may be smooth and unobservable from the outside. As the object approaches the critical mass, its compactness, mass divided by radius, grows closer and closer to that of a black hole. Its light-bending properties become extreme, its surface redshift increases, and the region from which light can escape narrows dramatically. Yet, as long as no event horizon forms, it's still technically a Q-star, a star made of force, not flame. But how do we know when the event horizon forms? Is there a sharp, discrete moment, a line across which a scalar field can no longer hold itself together? Or does the collapse proceed in a way that hides the formation of the horizon within the field itself, making it effectively invisible to outside observers? This is where quantum gravity may play a crucial role. In classical general relativity, once a certain compactness threshold is passed, an event horizon must form. But in many quantum gravity models, including loop quantum gravity and certain string-inspired frameworks, gravitational collapse may behave differently at ultra-high densities. Quantum pressure or topological effects might prevent the formation of a true singularity, or even a true event horizon, leading instead to black hole mimickers, objects that look like black holes but remain horizonless. In this view, Q-stars could occupy a strange gray zone, technically not black holes, but so compact and redshifted that no current telescope could distinguish them from one. The difference might only become apparent in the gravitational wave signals they produce, or in the absence of the ring-down behavior expected from event horizon formation. Another possibility arises from critical phenomena in gravitational collapse. In this framework, Q-stars may be part of a continuous family of solutions, with a critical point marking the divide between dispersion and collapse. Slightly below the critical mass, the field configuration disperses or oscillates. Slightly above it, the field collapses to form a black hole. Right at the critical point, the system hovers in an unstable equilibrium, perhaps the brief flash of a Q-star born and destroyed in the same heartbeat. And yet, even this division may be complicated by rotation. When angular momentum is introduced, it can support more mass, much like rotating neutron stars can be heavier than static ones. A rotating Q-star may be able to resist collapse longer, storing angular momentum in the scalar field itself. But rotation also introduces instabilities, frame-dragging effects, ergoregions, and possibly scalar instabilities that could hasten collapse. These effects are deeply nonlinear and difficult to model fully, but they suggest that the boundary between Q-star and black hole is not just a line, it's a landscape. What would the collapse of a Q-star look like if it happened? It might be abrupt, an implosion that concentrates the field into a singularity, forming an event horizon in a flash of gravitational radiation. Or it might be staggered, perhaps involving mass ejection, or a kind of scalar radiation as the field sheds excess energy before succumbing to gravity. In either case, the event horizon would form, cloaking the final stage from the universe forever. Until then, Q-stars might exist as pre-horizon objects, their surfaces hovering just shy of their Schwarzschild radius, their identities teetering between star and hole. This makes them more than just stellar oddities. They are laboratories of gravity, places where the universe practices becoming a black hole but never quite gets there. So where does a Q-star end and a black hole begin? The answer is still being written, equation by equation, simulation by simulation, and perhaps someday, observation by observation. It is the question of a line not drawn in chalk, but etched in quantum space-time. The story of how Q-stars might come into existence is as mysterious as the stars themselves. These exotic objects, stellar remnants sustained not by atomic pressure but by scalar fields, require conditions so extreme and specific that their formation demands a deep look into both the catastrophic deaths of normal stars and the primordial chaos of the early universe. In fact, Q-stars may have multiple potential origin paths, and understanding them could illuminate more than just their existence. It might unravel clues about the unseen architecture of reality itself. Let's begin with the more familiar of the two scenarios, the death of massive stars. Neutron stars, as we understand them, form in the violent aftermath of supernovae. When a massive star exhausts its nuclear fuel, gravity takes over and the core collapses. If the mass is below a certain threshold, electron degeneracy pressure can halt the collapse and leave behind a white dwarf. For more massive stars, the electrons are crushed into protons, forming neutrons, and neutron degeneracy pressure can then support the remnant. This is how neutron stars are born. But what if the collapsing star's core is just slightly too massive for a neutron star, yet not quite enough to tip into full black hole formation? Traditionally, this scenario results in a black hole. End of story. However, if scalar fields exist in nature, and if conditions allow them to condense into a coherent configuration during the collapse, the situation may take a radically different turn. Rather than forming a black hole, the collapsing core might settle into a new equilibrium, a Q-star. During the collapse, the density, curvature, and energy could become so intense that quantum fields, particularly scalar fields that might otherwise remain dormant, become activated. Instead of degeneracy pressure saving the core, it is the emergence of a stable scalar field configuration that halts collapse. This transition could occur in stars with masses just above the neutron star limit, creating what might be called post-neutron compact stars, not matter-based at their core, but field-based. In essence, a Q-star could be the next tier of compact object beyond neutron stars, occupying the mass gap that sits just before black hole formation. This pathway implies that Q-stars could be endpoints of stellar evolution, rare, perhaps, but naturally occurring in the universe wherever massive stars collapse just shy of the black hole threshold. If so, we might expect to find them masquerading as black holes in binary systems, especially those where the inferred mass is just slightly higher than what a neutron star should be, yet no definitive event horizon can be detected. However, this isn't the only formation channel. There's another, even more tantalizing possibility. Q-stars might not be born from death, but from the beginning of everything. To understand this, we must go back to the early universe, a time when the cosmos was an ocean of energy fields, particles, and quantum fluctuations. In the moments after the Big Bang, long before atoms formed, before stars ignited, and before matter as we know it even existed, the universe was dominated by quantum fields. Scalar fields, in particular, played a critical role in many theories of cosmic inflation, symmetry breaking, and phase transitions. In these earliest moments, the energy densities and space-time curvatures were unimaginably high. It's in this chaotic backdrop that primordial Q-stars might have formed. If certain regions of space underwent local scalar field condensation, either due to inhomogeneities, quantum tunneling, or topological defects, these regions could collapse under gravity and stabilize into compact, field-dominated configurations. Unlike ordinary matter, which clumps through atomic and nuclear interactions, scalar fields can self-organize through the structure of their potential energy. These self-bound configurations, if stable enough, would become isolated islands of field in the expanding universe. These would be primordial Q-stars, ancient objects formed not from dying stars but from the raw energy of the early cosmos. Because scalar fields may not interact strongly with light or regular matter, these objects would be nearly invisible, dark, compact, and lingering in the shadows of the universe. Over billions of years, they could remain undisturbed, acting like gravitational anchors, perhaps even contributing to the dark matter budget of the universe. If this scenario is correct, then Q-stars could be as old as the universe itself, possibly numbering in the trillions, drifting silently in galactic halos or hiding in intergalactic voids. Some might be no larger than asteroids in mass, others as massive as several suns. These primordial Q-stars would never have been hot, never fused hydrogen, and never undergone nuclear processes. They would be the quietest stars, born not from collapse but from initial condition, echoes of a quantum dawn. A third, even more speculative pathway involves phase transitions within neutron stars themselves. Suppose a neutron star accumulates mass over time, perhaps by accreting from a binary companion. As it crosses the upper mass limit, it's generally thought to collapse into a black hole. But what if, in the extreme interior of such a star, the energy density reaches a critical value where a scalar field nucleates spontaneously? Instead of collapsing into a singularity, the core undergoes a quantum phase transition, converting from nuclear matter to scalar field matter, and forming a Q-star at the center of the neutron star. This hybrid structure could lead to mixed-phase stars, partly made of normal matter, partly composed of scalar fields. Over time, the scalar field could eat the nuclear matter from within, converting the entire star into a Q-star. This would suggest a slow metamorphosis, not an abrupt transition, stars gradually changing their nature from particle-based to field-based. If such transitions are possible, then Q-stars could be hiding within ordinary neutron star populations, waiting to be discovered through their subtle deviations in mass-radius relations or thermal evolution. All of these formation pathways, collapse remnants, primordial structures, and phase transition products, suggest that Q-stars could arise in multiple contexts, governed by the availability of scalar fields, the mass energy conditions, and the quantum dynamics of gravity. In a way, their formation might mirror the fundamental duality of the universe itself, birth from destruction, and birth from nothing. If they form from the deaths of massive stars, Q-stars are the ashes of atomic fire, reborn in quantum configuration. If they form from the early universe, they are prestellar fossils, remnants of a time before particles, before light, before time moved in straight lines. Either way, they are relics of transformation, standing at the crossroads between matter and field, gravity and quantum mechanics, reality and possibility. And so the cosmic evolution of Q-stars remains an open book, one filled with explosions, equations, and the quiet pulse of scalar waves in the dark. If we trace the timeline of the cosmos backward to its very beginning, we enter a realm not dominated by stars or galaxies, but by fields, raw, untamed, and saturating every inch of the infant universe. In this early landscape, just fractions of a second after the Big Bang, the forces that shape our universe today were still settling into their identities. Space was not calm or cold, but a roiling quantum cauldron of unimaginable temperature, pressure, and energy density. And it is precisely in this exotic era that Q-stars, these hypothetical stars composed not of matter, but of organized force, may have quietly formed. Unlike neutron stars, which are forged in the death throes of massive stars, Q-stars may have no such ancestry. They might be older than stars themselves. If scalar fields, fields that assign a single value to every point in space and time, truly exist as fundamental parts of the universe, then the early universe would have been the perfect place for them to dominate. This is especially true if the scalar fields had self-interacting properties, which would allow them to condense into localized blobs of energy rather than spreading evenly through space. In those first microseconds after the Big Bang, matter as we know it hadn't yet condensed. Quarks and leptons, let alone protons, neutrons, or atoms, were still forming. But scalar fields could already have existed, responding to fluctuations in density and curvature. If a patch of this field condensed just the right way, through a combination of gravitational attraction and internal field dynamics, it could have created a stable pocket of energy, a compact region where the field coalesced into a gravitationally bound, horizonless object. That pocket would become a primordial Q-star. The process might resemble how topological defects form in field theories. During a phase transition, where a field cools and settles into a lower energy state, different regions may choose different configurations. The boundaries between these regions, where the field cannot smoothly adjust, can trap energy, creating defects like cosmic strings, domain walls, or monopoles. Q-stars, in this context, could be seen as topological solitons, stable field structures that resisted dissipation in the early universe. These early Q-stars would have no atoms, no crusts, no fusion. They wouldn't shine or burn. Instead, they would simply be bound configurations of field energy, stabilized by the interaction between gravity and the scalar field's own self-attraction or quantum charge conservation. Their structure could form in a way analogous to boson stars, but under even more extreme conditions, with field potentials shaped by the high-energy physics of the Big Bang. Crucially, if such objects formed in large numbers, they could have persisted until today, silently surviving the cosmic evolution that swept away less stable formations. While galaxies formed, stars were born, and planets cooled, Q-stars could have remained mostly unchanged, quiet, cold, and largely invisible. They would have no electromagnetic signature. They wouldn't undergo nuclear processes. And unless disturbed, they would remain gravitationally quiescent, floating through the dark. This leads to a compelling question. Could some of the dark matter in the universe actually be primordial Q-stars? It's a hypothesis that has intrigued theorists. Q-stars made of scalar fields that interact only weakly with normal matter would be a perfect candidate for non-baryonic dark matter. Unlike traditional dark matter particles, which are expected to be microscopic, Q-stars would be macroscopic dark objects, perhaps the mass of a planet or star, but with none of the visibility. They might even help explain certain anomalies in gravitational lensing. Observations of microlensing events, where a dark object passes in front of a distant star and bends its light, have sometimes revealed compact lenses with no visible mass. While black holes and brown dwarfs are candidates, Q-stars could also fit the profile. Their gravitational influence would match that of a star-sized object, but they'd emit no radiation and reveal no surface, no flicker, no flash. Just mass and motion. The early universe connection also raises another thrilling possibility. Some Q-stars could predate cosmic inflation itself. If scalar fields existed prior to or during inflation, and if local field fluctuations were preserved as inflation stretched space, then some of these field configurations could have been frozen into place, blown up from quantum scales to macroscopic sizes. When inflation ended and reheating began, those pockets of trapped energy could have become gravitationally bound and stabilized into Q-stars. That would make them older than the observable universe, in a sense, not just relics of the early cosmos, but of pre-cosmos. Even more intriguingly, these ancient Q-stars might retain quantum imprints from their formation, subtle fluctuations or patterns in their structure that encode the field dynamics of the primordial universe. If we could somehow probe one, perhaps by measuring the gravitational waves emitted during rare interactions, it might offer us a window into physics far beyond the reach of our current particle accelerators. A Q-star could be a cosmic fossil, not made of rock or gas, but of pure theory locked into form. And what of their distribution? If they formed in the early universe, they would not be confined to galactic disks or stellar nurseries. They might be scattered throughout the dark matter halos of galaxies, orbiting invisibly, or drifting in intergalactic space like ghosts. Some might be near us right now, perhaps even passing through our solar system, unnoticed except for their gravitational tug. Could we ever detect such a thing? Maybe through microlensing, as mentioned. Or perhaps through gravitational wave echoes, if two Q-stars collided or merged. Such a merger would not produce the ring-down signature of black holes, but a different waveform, potentially with telltale features that betray the absence of an event horizon. Or perhaps we might detect subtle timing anomalies in pulsars, if a Q-star passed near one and distorted the spacetime around it. One day, if technology permits, we may learn to listen for these dark whispers in the gravitational fabric of the universe. And if we do, we might find that some of the oldest structures in existence are not galaxies or quasars or even black holes, but Q-stars, quiet remnants of a time before time, still humming with the order they found in a universe that had none. Across the dark canvas of the cosmos, there are objects, massive, dense, gravitationally powerful, that emit no light, absorb no heat, and betray no surface. We see their presence only through gravitational effects, how they tug on stars, bend light, or warp time. These are the ghost stars of the universe, mysterious, invisible bodies haunting the edges of astrophysical knowledge. While we often attribute such phenomena to black holes or dark matter clumps, what if some of these phantoms are not holes in spacetime, but quantum stars without flame? Could Q-stars be the true culprits behind at least some of the universe's most confounding shadows? Let's begin with what we know. Many astrophysical observations reveal objects that behave like compact, massive bodies but do not emit the electromagnetic signatures we would expect. For instance, surveys using gravitational microlensing, the bending of light by an unseen object between Earth and a distant star, have occasionally reported masses too large for planets, but with no visible counterpart. These could be black holes, yes. But black holes require an event horizon, a point of no return, and not all these objects fit that profile perfectly. Enter Q-stars, whose lack of an event horizon allows them to mimic black holes in terms of mass and compactness, while still being fundamentally different inside. They could be dark, dense, and horizonless, precisely the type of object that would bend light, tug on nearby stars, or influence stellar dynamics, all without emitting a single photon of their own. Unlike neutron stars, they wouldn't radiate strongly in X-rays. Unlike white dwarfs, they wouldn't glow visibly. And unlike black holes, they wouldn't exhibit characteristic accretion disk emissions unless under very specific circumstances. This means Q-stars might be hiding in plain sight, in binary systems where the companion star seems to orbit an invisible mass, or at the center of some galaxies where something is causing gravitational lensing, but no light source is visible. In fact, some X-ray binaries thought to host black holes could, in theory, harbor Q-stars. If the object is compact enough to create strong tidal effects and disrupt its companion star, but lacks the exact radiative behavior of a known black hole, it might be something far more exotic, a Q-star impersonating a black hole in every way except the final step of true event horizon formation. Some gravitational wave detections, too, may raise questions. LIGO and Virgo have recorded waves from compact binary mergers, mostly attributed to black hole or neutron star pairs. But the waveforms, especially in rare or unexpected cases, could include subtle deviations that hint at a different internal structure. A Q-star merger might emit a slightly different gravitational wave signal, particularly in the post-merger phase. If a horizon never forms, there could be gravitational wave echoes, reverberations from the collapse and bounce of a horizonless body, rippling back outward into space. Astrophysicists have proposed this very idea, that post-merger echoes and gravitational wave events could indicate exotic compact objects, ECOs, a broad category in which Q-stars comfortably sit. These echoes haven't been definitively observed yet, but data reanalyses occasionally suggest patterns that standard black hole models struggle to explain. If confirmed, even once, such a signal could be the death knell for classical black hole dogma, and the coronation of something stranger. Let's also consider the dark matter problem. One of the universe's biggest mysteries is why galaxies rotate faster than they should, and why galaxy clusters remain bound despite visible matter falling short. This points to the presence of nonluminous mass, what we call dark matter. Usually, this is assumed to be made of weakly interacting particles. But what if part of the solution lies in compact dark objects scattered throughout the cosmos? If Q-stars formed in the early universe and survived to this day, they could contribute significantly to the dark matter content of galactic halos. These Q stars wouldn't clump like normal stars. They wouldn't emit radiation or heat. They wouldn't participate in chemical evolution. But they would pull. They would bend light. They would stabilize galaxies just as dark matter seems to do. And because their composition is non-baryonic, not made of standard atomic matter, they wouldn't violate known dark matter constraints. In fact, Q stars may be one of the only macroscopic objects that could behave like gravitationally active, optically invisible dark matter. Another realm where Q stars could explain enigmas is in hypercompact stellar remnants. Some astrophysical systems show signs of unusually dense, massive remnants with no clear emission. In cases where we would expect to see a neutron star cooling or radiating in X-rays, we find only silence. If Q stars formed from neutron star collapse or field phase transitions, these could be such remnants, frozen spheres of quantum force, indistinguishable in mass but lacking the nuclear matter behavior that would make them visible. Even certain quiescent galactic centers, those that seem too massive to be neutron stars, yet emit no activity typical of black holes, could harbor Q stars. If they don't accrete matter at a high enough rate, they wouldn't shine in X-rays. But their mass would still curve spacetime dramatically, lend starlight, and influence stellar motion around them. Of course, not all mysteries point to Q stars, and it's important not to use them as a catch-all answer. Many dark astrophysical phenomena can be explained through more conventional means. But the range of unexplained observations, from microlensing anomalies and gravitational wave signals, to dark compact halo objects and invisible galactic companions, suggests that we're likely missing part of the cosmic picture. Q stars offer a coherent, theoretically grounded explanation that could fill in some of those blanks. The key is to keep looking, for indirect gravitational fingerprints, for strange timing signatures in pulsars, for anomalies in binary star systems, for echoes in the space-time ripples of colliding masses. If Q stars are real, their ghostly presence will eventually betray them. And when that happens, we may realize we've been watching ghosts all along, stars that never lived by the rules of matter, that shine not in light, but in the gravitational whisper of hidden fields. The universe speaks in many voices, but some are barely whispers, waves not of light, but of space-time itself. If Q stars exist, their language may not be electromagnetic radiation like ordinary stars, but something far subtler, gravitational waves, scalar field oscillations, and perhaps even bursts of exotic energy that conventional detectors struggle to recognize. These hypothetical objects may live in silence, but they are not mute. They could send out signals unlike anything we've cataloged, if we're wise enough to listen. Unlike neutron stars, which pulsate with electromagnetic radiation, or black holes, which roar in gravitational waves when they collide, Q stars may radiate in silence, their presence betrayed only through rare and strange disturbances. And these disturbances could, if correctly interpreted, offer an unmistakable fingerprint of a star not made of matter, but of quantum force. One of the most promising avenues for detection is through gravitational waves. These ripples in space-time are generated by accelerating masses, especially during violent events like binary mergers. The LIGO and Virgo collaborations have opened a new window into this realm, detecting dozens of compact binary coalescences involving neutron stars and black holes. But in between those categories lies a curious possibility: the merger of two Q stars, or a Q star with a neutron star or black hole. From a distance, the inspiral of a Q star might look very similar to that of two neutron stars or small black holes, until the final moments. That's where the key differences lie. If a Q star is horizonless, then when it collides, the result is not a black hole with an immediate ring-down phase, but potentially a bouncing, oscillating, or metastable remnant. This could create gravitational wave echoes, faint repetitions of the original wave signal, caused by waves bouncing inside the object's structure or reflecting off its dense inner geometry. Echoes like these have been a topic of growing interest in theoretical physics. While they haven't yet been definitively observed, some gravitational wave data have hinted at post-merger anomalies, features not easily explained by classic black hole models. Q stars, with their unique internal field dynamics and lack of an event horizon, could naturally produce such echoes. Instead of absorbing all perturbations like a black hole, a Q-star might ring, like a bell, its scalar field reverberating through space-time. Beyond mergers, Q-stars might also radiate through non-catastrophic oscillations. Just like neutron stars can undergo starquakes or magnetic reconnection events, Q-stars could experience internal field instabilities, causing their scalar configuration to momentarily shift and re-equilibrate. This might lead to pulses of gravitational radiation, albeit subtle and extremely difficult to detect without very sensitive instruments. These silent flares wouldn't show up in X-rays or gamma rays, but they might leave ripples in the gravitational field. Even more fascinating is the idea that Q-stars could decay or transform over long timescales. If some configurations are only metastable, they could eventually tunnel to a lower energy state, especially if nudged by a nearby gravitational interaction. Such a quantum decay process might release a sudden burst of energy, perhaps not in light, but in a spray of scalar particles or an asymmetric gravitational wave signal. The event would be silent in the electromagnetic spectrum, but not invisible to the right ears. There's also a chance that Q-stars could be sources of high-energy phenomena, but in a form we haven't yet classified. If the scalar field interacts even weakly with regular matter or other fields, then under the right conditions, a Q-star could radiate through unusual processes, exotic particle production, scalar photon conversion in magnetic fields, or rare gamma-ray bursts with peculiar profiles. These emissions would be non-thermal, perhaps appearing as brief spikes or soft flashes without any accompanying radiation. We might already have observed such events, cataloged them as unclassified transients, or failed GRBs, without realizing they were signatures of something new. Moreover, if a Q-star is rotating, it may emit continuous gravitational radiation due to asymmetries in its scalar field configuration. Like pulsars, rotating Q-stars could send out a constant signal, not in radio, but in gravity. These monochromatic gravitational waves would be incredibly faint, but detectable over time with next-generation detectors like LISA or the Einstein telescope. Identifying one would be revolutionary, a steady gravitational tone from a star with no light. It's also worth considering indirect signals. If a Q-star is in a binary system, its gravitational field would affect its companion's motion in subtle ways. Over time, careful timing of a pulsar companion or spectral shifts in a stellar partner could reveal deviations from expected orbital dynamics. These deviations, small differences in redshift, tidal distortion, or orbital decay, might point to a compact object with no surface and no horizon. The smoking gun? A mass too high for a neutron star, too low for a black hole, and with no evidence of an accretion disk or jet. And then there's the possibility of scalar wave detection. If Q-stars radiate scalar field fluctuations, they might produce disturbances in space not detectable by electromagnetic or traditional gravitational wave observatories, but perhaps by future instruments designed to detect exotic fields. Some experimental setups are already testing for such effects: ultra-sensitive interferometers, scalar field coupling detectors, or dark matter wave experiments. A sudden shift in these detectors, especially coinciding with a known gravitational event, could be the first indirect confirmation of a Q-star's hidden breath. But perhaps the most haunting part is this: the signals may already be in our data. A microlensing event with no optical counterpart. A pulsar with an unexplained glitch in timing. A gravitational wave that echoes long after the main event. A soft gamma-ray pulse from nowhere, with no afterglow. These anomalies, these oddities, we may have dismissed them, overlooked them, or categorized them under unresolved. But what if they are all connected by a common source? Q-stars may not shine. They may not roar. But they might hum, pulse, and tremble, leaving behind a trail of ripples in the silence. And if we tune our instruments, and our imagination, just right, we might finally hear them. Pulsars are among the most precise and reliable beacons in the cosmos. These rapidly rotating neutron stars emit beams of electromagnetic radiation, usually in radio, X-ray, or gamma-ray wavelengths. From their magnetic poles, sweeping across Earth like the beam of a cosmic lighthouse. Their pulses are so regular, they rival atomic clocks in timing accuracy. But despite decades of study, many questions about pulsars remain unanswered. Some spin faster than our models predict. Others have unusual magnetic fields, strange glitch behavior, or unexpected radiation profiles. So we must ask, could some of these neutron stars actually be something else entirely? Could some pulsars be Q-stars in disguise? It's a question that takes us deep into the interface between observational astronomy and theoretical physics. At first glance, pulsars appear to fit well within the neutron star model. Their masses are typically between 1.4 and 2 solar masses, and their radii hover around 10 to 15 kilometers. They emit strong magnetic fields and rotate with astonishing speed, sometimes hundreds of times per second. All of this fits nicely into the neutron star framework, supported by neutron degeneracy pressure and anchored in the physics of dense nuclear matter. But here's the twist: none of this excludes the possibility of a Q-star. In fact, a Q-star made of exotic scalar fields could replicate all of these characteristics: mass, size, compactness, even rapid rotation, while having a completely different internal structure. From the outside, a Q-star might emit periodic pulses, just like a neutron star, if its field configuration supports magnetic-like behavior or if surface-like phenomena develop. If the scalar field carries a conserved charge or angular momentum, it could very well radiate in bursts or beams aligned with its rotational axis. Thus, the pulsar signal alone does not rule out Q-stars. Let's explore how this might work. Imagine a Q-star formed from a scalar field that allows for rotation and localized oscillation. These oscillations could be periodic, resulting in time-varying mass quadrupoles, perfect for emitting gravitational waves. If this object also has a mechanism to couple its scalar field to electromagnetism, even weakly, it could emit pulses of electromagnetic radiation as it spins, very much like a traditional pulsar. The pulse wouldn't necessarily be powered by nuclear physics or crustal dynamics, but by oscillations in the quantum field itself. And now the comparison becomes intriguing. Some pulsars, especially the so-called millisecond pulsars, rotate incredibly fast, faster than any neutron star should be able to spin without breaking apart. While this is often attributed to spin up from accreting matter in binary systems, there are edge cases that push the boundaries of theoretical neutron star stability. A Q-star, on the other hand, might sustain faster spin rates due to the fluidity of its internal field and the lack of a rigid crust. Its structural stability could arise from the balance between scalar field energy and gravitational binding, not from rigid matter layers, allowing for ultra-rapid spin without disintegration. Another point of interest: pulsar glitches. These are sudden, unpredictable changes in the rotational period of pulsars, small speedups that are still not fully understood. In neutron star theory, glitches are thought to be caused by starquakes in the crust or by sudden shifts in the superfluid interior. But what if some glitches are instead due to shifts in a scalar field configuration within a Q-star? A slight reorganization of the internal field structure, like a mode transition or phase flip, could alter the moment of inertia and produce a similar observable effect. In this sense, glitches might not be mechanical but quantum field phenomena, reframed through the lens of exotic matter physics. Now consider the magnetar family of pulsars, neutron stars with unimaginably strong magnetic fields, trillions of times more powerful than Earth's. Magnetars occasionally release massive bursts of X-rays and gamma rays, including giant flares whose power rivals that of supernovae, but without the accompanying collapse. These behaviors are not easily explained by standard nuclear physics, and some theorists suggest that something more exotic may be at play. If Q-stars possess scalar fields coupled to electromagnetism in unusual ways, they could create similar effects, releasing enormous energy when the field momentarily destabilizes or realigns. In this context, the periodicity we observe in pulsars might simply be the signature of a spinning Q-star with internal oscillations, its pulse, arising not from rotating matter, but from a stable, rotating field configuration with a directional energy output. And if Q-stars can support persistent field modes, oscillations that do not dissipate easily, then these pulses could be far more stable over time than those from material-based crusts. The legendary timing precision of pulsars, then, may not just be a feature of neutron matter, but perhaps of self-sustaining quantum fields. Let's go one level deeper. Q-stars could also explain certain timing anomalies in pulsar data, small irregularities or fluctuations in pulse arrival times that don't match expectations. While often attributed to binary companions, interstellar medium effects, or timing noise, some of these may hint at deeper complexities. For instance, if a Q-star's scalar field is not entirely uniform but slightly time variable, it could introduce tiny shifts in the emitted pulse signature, subtle fingerprints of field fluctuations leaking into observable space. Then there's the possibility of hybrid stars, objects with a neutron star shell and a scalar field core. In this model, a Q-star might start as a neutron star, but undergo a phase transition in its core, converting part of its mass into a scalar field configuration. The outer layers could remain neutron-rich matter, while the interior is stabilized by exotic fields. Such a hybrid could radiate like a pulsar but behave differently in certain conditions, such as during collapse, spin-down, or thermal evolution. In this case, some known pulsars might already be hybrids on the evolutionary path toward becoming full Q-stars. Let's not forget, most of our conclusions about pulsars are inference-based, not direct observations. We cannot see a pulsar's surface. We cannot probe its core. We reconstruct its properties from pulses, timing, and radiation profiles. And therein lies the possibility for mistaken identity. If Q-stars can imitate the external behavior of neutron stars, even closely, then they could be lurking within pulsar catalogs, misclassified by assumption. So how might we tell the difference? Perhaps through gravitational wave signals, if one of these stars merges. Perhaps through pulse timing variations, if scalar field effects emerge. Or perhaps, someday, by observing a pulsar that should have collapsed into a black hole based on its inferred mass, but hasn't. A horizonless, silent object that pulses with perfection, but never collapses. That's when we'll know, we've been listening to a Q-star all along. Q-stars occupy a strange place in the landscape of modern physics, hovering between the rigorous and the speculative, between established theory and the edge of imagination. They are not merely science fiction, their existence is rooted in real, plausible extensions of our current understanding of quantum field theory and general relativity. And yet, no one has ever seen one. No telescope has definitively caught their signal. No detector has confirmed their merger. Still, despite this absence of direct evidence, physicists continue to take Q-stars seriously. Why? Because they solve problems. They fill gaps. They offer alternatives when traditional models come up short. And most of all, they arise naturally, not as forced constructs, but as consequences of well-motivated theories that extend our current physics in ways we're already exploring for other reasons. At the heart of this is the simple realization: our universe may be governed not just by particles, but by fields, smooth, invisible energy landscapes that pervade all of space. In the standard model of particle physics, most forces and particles arise from such fields. The electromagnetic field, the Higgs field, even the gravitational field itself, all of them are fields first, particles second. Q-stars embrace this framework. They're not made of atoms, but of concentrated, self-contained regions of exotic scalar fields, energy locked into gravitational balance. And scalar fields are not just theoretical playthings. The Higgs field is a scalar field. Some models of dark energy invoke scalar fields. Inflation, the rapid expansion of the early universe, is often modeled using an inflaton scalar field. These fields already form the bedrock of key theories in high-energy physics and cosmology. So when physicists propose that under the right conditions, a scalar field could clump into a compact, stable object, a Q-star, it doesn't seem outlandish. It seems like a logical extrapolation of physics we already trust. Moreover, the mathematics supports their stability. Q-stars aren't just fleeting phenomena. Certain configurations of scalar fields appear to be long-lived or even eternally stable in simulations. They don't require fine-tuning or artificial conditions. Depending on the field's properties, its potential energy landscape, its self-interactions, or conserved charges, the resulting object can reach a state of equilibrium. Gravity pulls inward, the scalar field pushes outward. The result is a star with no surface, no fusion, and no collapse. Just balance. Quiet, eternal balance. Physicists are especially intrigued because Q-stars sit in a gap in the stellar zoo that feels conspicuously empty. Between neutron stars and black holes lies a mysterious no-man's land, a region where the pressure of neutron degeneracy can no longer hold back gravity, but where general relativity doesn't yet demand the formation of an event horizon. Theoretically, nothing in the laws of physics prohibits an object from existing in this in-between state, provided there's another form of pressure or repulsion to counter gravity. That's exactly what Q-stars offer. They provide a new mechanism, not thermal pressure, not degeneracy pressure, but quantum field pressure, or more precisely, the self-consistent behavior of scalar fields under gravity. If such fields exist, and if they can condense into localized energy lumps, then Q-stars are not just possible, they're inevitable. Of course, speculation must be tempered with caution. No direct observation of scalar field stars has been made. Many of the properties predicted for Q-stars, like their gravitational wave echoes or unusual compactness, are also consistent with other exotic objects, such as gravastars, boson stars, or even certain modified black hole models. The landscape of exotic compact objects is broad, and the lines between them are often blurry. Q-stars are one of many contenders in a race to explain what lies beyond the event horizon, or whether such a horizon is even necessary. Still, Q-stars hold a unique appeal because they connect so many pieces of modern physics. They touch quantum gravity, field theory, early universe cosmology, and astrophysics all at once. They offer a rare point of synthesis, where deeply theoretical work might manifest as a real, observable object in space. That's why research continues. Papers are published. Simulations are run. Alternative gravitational wave templates are built to match potential Q-star signatures. Observational anomalies, odd microlensing events, unexplained pulsar behaviors, strange compact mergers, are re-examined with Q-stars in mind. Every time our instruments improve, every time our data deepens, the question is asked again, is there something here we've missed? Physicists are also motivated by a deeper, philosophical impulse, the same one that gave us the Higgs boson, neutrino oscillations, and gravitational waves. The idea that the universe hides its truths in strange corners. That the most profound answers don't always come from what we see, but from what we suspect, what we calculate, what we dare to believe might be just beyond the edge of evidence. If Q-stars are real, they are stars of the future, not in time, but in concept. They don't shine with fire. They shine with theory. They challenge our definitions of what a star even is. And they invite us to imagine a cosmos where not all light comes from heat, and not all matter comes from atoms. They are theoretical, yes. But they are tempting, so tempting, in fact, that we may find we've already observed them without knowing it. All we need to do is look again, with new eyes, and a new model in mind. Imagine the moment a signal arrives, be it from a gravitational wave detector, a microlensing anomaly, or a precision pulsar observation. Scientists scramble to interpret it. The object is too massive to be a neutron star, yet it exhibits no event horizon. It emits no X-rays, no thermal glow, no radio pulse from an accretion disk. But its gravitational fingerprint is undeniable. This is no black hole. It's something else. And after meticulous modeling, elimination of all known possibilities, and confirmation from independent instruments, the conclusion becomes inescapable. We've found a Q-star. Such a discovery wouldn't just be the biggest news in astrophysics. It would be a revolution across multiple domains of science, a seismic shift in how we understand matter, energy, and the very fabric of the cosmos. First and foremost, it would validate the existence of scalar fields as real, physical components of the universe, not just mathematical tools or hypothetical constructs, but actual sources of mass and structure. While we already accept scalar fields like the Higgs, confirming that scalar fields can condense into stable, macroscopic objects would expand their role from particle physics into astrophysical structure formation. Fields would no longer just operate at the tiniest scales, they would shape stars. This would have immediate implications for quantum field theory. The theories that predict scalar fields often emerge from beyond standard model physics, including supersymmetry, string theory, and quantum gravity frameworks. Discovering a Q-star would offer a rare observational touchstone, experimental evidence that some of these exotic models describe not just mathematical playgrounds, but real-world phenomena. Parameters in scalar field potentials, once entirely theoretical, could be constrained or even measured. Particle physicists would gain a cosmic laboratory for field dynamics too powerful to recreate on Earth. But perhaps even more profound would be the impact on general relativity and our understanding of gravity. Up until now, general relativity has been wildly successful at explaining large-scale gravitational behavior, from planetary orbits to black holes and cosmological expansion. But it leaves questions unanswered when pushed to its limits. The very idea of a black hole, with its infinite density and event horizon, suggests a breakdown of physics at the singularity. Quantum gravity is supposed to fix this, but we don't yet know how. Q-stars could provide the missing link. They show us that extreme compactness and mass don't require an event horizon. That quantum field effects, long considered negligible at large scales, can balance gravity and prevent collapse. This changes the game. It means we may not need to accept singularities at all. There may be a regime of stellar evolution where quantum structure prevents absolute gravitational dominance. In this way, Q-stars might point toward a unified picture of gravity and quantum mechanics, a theory where fields and curvature co-govern the shape of reality. And then there's the practical implication. The astrophysical zoo just got a new member. Textbooks would have to be rewritten. The classic progression, white dwarf, neutron star, black hole, would gain a new branch. Q-stars would become an object class in their own right, with distinct formation pathways, mass-radius relationships, and observational signatures. We'd need new catalogs, new classification systems, and new search strategies. Suddenly, whole categories of unclassified compact objects in our archives would be candidates for re-examination. Observational astronomy would surge with purpose, combing through data from missed signals and hidden Q-star footprints. It wouldn't stop there. Dark matter theories would come under renewed scrutiny. If scalar fields can stabilize into Q-stars, and if such stars can form under the extreme conditions of the early universe, then some fraction of dark matter might be macroscopic, not particles, but compact objects made of quantum force. This would challenge decades of particle-centric dark matter models and offer a whole new experimental frontier. Maybe Q-stars are the tip of the dark iceberg. Cosmology, too, would evolve. If Q-stars formed in the early universe, they could be used as probes of primordial field behavior, inflationary dynamics, and post-Big Bang thermodynamics. We might learn about the reheating phase, about symmetry breaking, or about conserved charges that have shaped cosmic evolution. Each Q-star could become a cosmic fossil, encoding physics from a time when the universe was barely seconds old. And then, of course, there's the impact on our philosophical view of the universe. We've long associated stars with thermonuclear fusion, with heat, fire, and light. But Q-stars would defy that. They'd be stars of balance, not combustion. Objects of internal symmetry and external silence. They wouldn't illuminate the night sky. They wouldn't host habitable zones or explode in supernovae. Instead, they would be stellar sculptures of pure field dynamics, humming with invisible forces, challenging us to see with instruments tuned not to light, but to the gentle undulations of spacetime itself. They would remind us that the universe is not limited to what we can see, or even what we can imagine. That sometimes, the most astonishing structures are not made of atoms, or even matter, but of mathematics come alive. The day we find a Q-star, everything changes. Our models of stellar death and collapse evolve. Our assumptions about compact objects are rewritten. The boundary between particle physics and astrophysics dissolves. The theoretical becomes tangible. And the invisible becomes undeniable. We would no longer be asking, "What is a Q star?" We would be asking, "How many have we already missed?" In a universe ablaze with light, it's easy to forget that not every star must burn. Some stars, perhaps the strangest of all, are not born in the throes of nuclear fusion, not forged in collapsing clouds of gas and dust, but in the abstract realms of theory, in the curvature of space-time and the silent hum of quantum fields. They do not illuminate galaxies. They do not host solar systems. They do not go supernova, seeding the cosmos with heavy elements. Instead, they reside in the margins of our equations, quietly waiting for our understanding to catch up with their existence. Q stars are not stars in the way we've come to define them. They are not flame and fury, not heat and pressure. They are the perfect antithesis of what we expect, cold where others are hot, smooth where others are layered, stable not through brute force, but through elegance. Held together not by atoms, but by the balance of gravity and the gentle push of scalar fields, they represent a different kind of cosmic equilibrium, a balance born of mathematical precision rather than elemental chaos. And that's what makes them beautiful. To discover a Q star, or even to truly believe in the possibility of one, is to admit that nature doesn't just build with the bricks of matter, but with the architecture of ideas. It is to accept that the universe may be as much thought as it is thing. That perhaps, somewhere in the silence between black holes and neutron stars, there lies a form sculpted not by the violence of collapse, but by the subtle logic of the quantum. These stars challenge us not just to look harder, but to think deeper. They remind us that the cosmos is not merely a physical place, but a conceptual one, that understanding it requires not just observation, but imagination. They are stars in the truest poetic sense, guiding lights, not of navigation, but of intellectual direction. Points not of heat, but of wonder. If Q stars are real, they have always been out there, drifting in the darkness, undetected, overlooked, misclassified. Their existence would mean that the universe has been whispering secrets for eons, and we are only just now learning to hear them. And if they are not real, if they are nothing more than mathematical ghosts, then even still, they have served a noble purpose. They have expanded the boundaries of our curiosity, challenged the rigidity of our models, and given us a reason to ask better questions. In the end, whether we find them or not, Q stars will continue to flicker in the minds of physicists, as enigmatic symbols of what might be. Because the pursuit of truth is itself a kind of illumination, and in that light, Q stars shine brilliantly. Perhaps the strangest stars are not born in fire, but in equations, flickering not with light, but with the mind's pursuit of the unknown. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.